So, I think we can start. Dear colleagues, today we start our 3-day conference for memory of Professor Zhilyaev. By this event, we want to pay respect to Professor Zhilyaev as a great scientist, wise teacher, and inspiring mentor. Today we start a cycle of free conference days. Every day we will start from plenary session. After that, we after short coffee break. After short coffee break, we start every day. We start sections with report. Dear colleagues, if before your speech during lectures, please switch off your microphones. You can ask your questions directly, and the first speaker is Alexey Korchunov, Vice Rector for International Affairs of North of Magnitogorsk State Technical University. You are welcome.
Dear colleagues, good morning, good afternoon, or maybe good evening. It depends on the time zones. It's very big pleasure to have welcome speech today. On behalf of the administration of North of Magnitogorsk State Technical University and the organizing committee, we are delighted to welcome you to the Magnitogorsk Materials Week conference, which is dedicated to the memory of Professor Alexander Petrovich Zhilyaev. Professor Zhilyaev has been a visiting scientist at our university in the frame of a government mega grant and has made a significant contribution to the development of the scientific and international activity in our university. He established International Laboratory of Mechanics of Gradient Nanomaterials that currently bears his name. Several years ago, Professor Zhilyaev proposed the idea to hold Magnitogorsk Materials Week workshop. With his active participation, the International Scientific Youth Conference Magnitogorsk Rolling Practice has received a new impulse. And today, Magnitogorsk Materials Week is one of the interesting international events in our university. For our students and the researchers, it's a good opportunity to listen to the reports of leading scientists and discuss about current trends and new aspects in severe plastic deformation of metallic materials. The fifth Magnitogorsk Materials Week workshop is held in the format of a scientific conference. As can we see, the agenda of the conference is very intensive and indicates the deep appreciation that Professor Zhilyaev had in the scientific community. Professor Zhilyaev was a famous scientist in material science and very friendly man. For our university, it is very important to maintain and develop his scientific heritage and his projects. We are sure that the conference will give a new impetus to a wider collaboration between participants and promote to build new international scientific teams. We hope you will have fruitful time during the conference, and we are always glad to see you in guest-friendly city Magnitogorsk after COVID restrictions. Dmitry, thank you.
Thank you. The second speaker is Professor Raab from Ufa State Aviation Technical University, and the second place is the Laboratory of Mechanics of Gradient Nanomaterials, NMSTU. You're welcome.
Dear colleagues, I am glad to see you all at the conference in memory of Alex Zhilyaev. Alex was and will be my good friend and scientific mentor, and I think not only mine. At Magnitogorsk Technical University, he, as a leading scientist, organized a scientific STEAM and problem laboratory, mechanics of nanogradient materials. This is one of the promising areas of nanotechnology on a global scale. The laboratory has been working successfully for 3 years. This is, we received new research equipment and invite everyone to cooperate. I hope our reports will allow you to decide on the topics of this cooperation. Let me announce the beginning of the conference and begin its work. Thank you.
Thank you, Professor Raab. A few words about our schedule. For Russian speakers, I ask you to rename yourself by English in chat of Zoom. We have every day we have plenary reports with for plenary reports. Plenary speakers have 30 minutes for report and 10 minutes for discussion. For reports in sections, you have 15 minutes for report and 5 minutes for discussion. Please be careful with the schedule because we have a lot of people from around the world, and as a result, we should finish every report in time. Actual program you can find on our website, matweek.com, and for some case, you can visit our YouTube translation. If we don't have places in Zoom room, we have a recording of this event, and we will record it on our YouTube channel and publish. So the first speaker is from UK. This is Professor Langdon, the close colleague of Professor Zhilyaev. Professor Langdon, you're welcome.
Anyway, good afternoon to everybody. Here we go.
Yes, we can see. You're welcome.
Well, good afternoon. Good morning in England, but good afternoon in Magnitogorsk. First of all, I want to thank everybody for inviting me to give this talk, and especially to give the first talk in this session. And I want to pass greetings to all of the people that I know in Magnitogorsk. I had the pleasure of visiting Magnitogorsk about 3 years ago, and I met many people, and I much enjoyed my visit, and I hope in the future there will be another opportunity to visit your city. Dr. Zhilyaev spent all his life working in the areas of superplastic properties and high pressure torsion. And therefore, I think my talk will be very appropriate for his memorial symposium. How do I go forward? There we go. I met Alex a long time ago, probably in 1989, when I made my first visit to Ufa, and we became friendly. And after that, we collaborated on many research topics, and we have many joint publications. And I should mention at this stage that we also co-authored a book. The book is by Valiev, Zhilyaev, and myself. It's called Bulk Nanostructured Materials, Fundamentals and Applications. and it was published by Wiley in 2014. I did some background on Alex. I looked at his publication record. This is his most cited paper, which appeared in Progress in Material Science. And it's the paper that he wrote with me. We wrote a review article on high pressure torsion and published it in 2008. And I noticed on Google Scholar, it now has 2,711 citations, probably more by now. This was about 2 weeks ago. So that is Alex's most cited paper. I had the pleasure also of inviting Alex to come and work with me in the United Kingdom. He came to the University of Southampton and stayed with me for about 2.5 years. And this gave an opportunity for us to participate in some foreign travel. And I want to show you some pictures. This is 2012 at the NanoMat conference in Sao Carlos, Brazil, in September 2012. Alex, of course, is here on the right. I'm sitting on the left. This is my wife, Maddie. This is Professor Zherebtsov and his wife from Austria. This is my old student, former student, Senji Harita from Japan, who will be participating in this meeting. And Yi Huang, my collaborator, who is now at the University of Bournemouth in the UK. So this was in Brazil in 2012. This is also in 2012. This is when I received the Acta Materialia gold medal, and the special symposium was held as part of the European MRS fall meeting in Warsaw, Poland. And here we are standing within the building of Warsaw University of Technology. Alex is here on the left. I am here. This is Roberto Figueiredo, who will be participating in this meeting. This is Yi Huang from England. This is Aicha Lusif, who is now at a university in Saudi Arabia. And the reason we're standing here is because this statue at the back is a statue of Marie Curie. Marie Curie, of course, was a very famous Polish scientist who obtained a Nobel Prize working in Paris. And this is her statue within the university. And here's another picture, Alex again, and I'm standing here. This is at the Pan American Materials Conference in Sao Paulo, Brazil, in July 2014. Yi Huang on the left. The second person from the left is Megumi Kawasaki, who will be the opening speaker tomorrow. Roberto Figueiredo on the right. So a lot of these people are connected with this meeting. Alex's main interest was superplastic flow because he worked at the Institute of Superplasticity in Ufa. And he also was interested in producing ultrafine grain materials, metals with very, very small grain sizes, using severe plastic deformation techniques such as high pressure torsion. And therefore, the first thing that we need to do is to define superplasticity. And I want to describe some of the results that we've obtained recently on a bismuth tin alloy processed using HPT. First of all, what is the definition of superplasticity? This is my definition taken from a paper in Journal of Material Science in 2009. And I will read it out to you. Superplasticity is the ability of a polycrystalline material to exhibit in a generally isotropic manner very high elongations prior to failure. The measured elongations in superplasticity are generally at least 400%, and the measured strain rate sensitivities are close to 0.5. Now, these two numbers are important because we can take materials that are deforming by other mechanisms that are not superplastic, for example, by viscous glide, and then you have elongations that can be up to 300%. but the materials are not superplastic and the strain rate sensitivities are about 0.3. So it's very important that you look for the elongation of at least 400% and a strain rate sensitivity of about 0.5. Those will be the two characteristics that we need to look for. The very first report of superplasticity was actually in 1934, and it was by Pearson in England, and he used the bismuth tin near eutectic alloy and pulled it out. And amazingly, he got an elongation of 1950%. And the specimen was so long that he wound it into a coil, which you can see here in order to take this picture. And this is the first true example of superplasticity. There are no earlier reports of superplasticity in the literature. And here's the reference for this paper, Journal of the Institute of Metals in 1934. That was 85 years ago when it was in England, and you would think that people in England would be excited and they would work on superplasticity, but that didn't happen, because in fact, this result was picked up in the Soviet Union, and it was within the Soviet Union that most of the work was then carried out over the next few years. And it's interesting that the main person in the Soviet Union was Bokvar and his colleagues. And it's a translation of the work of Bokvar that gives us the word superplasticity. It's a translation of this word. I won't try to pronounce it in Russian, but apparently it means ultra-high plasticity. And when it was translated into English, they used the word superplasticity. And the very first publication of this word in English is in 1947 in Chemical Abstracts. And here's a translation of a paper by Bokvar in the Bulletin of the Academy of Sciences in Russia. And they use the word superplasticity in zinc aluminum alloys. So there's the first example. The very, very first book on superplasticity was this one. And this was given to me, in fact, by the author, by Professor Pezhnyakov. It's in Russian, but it was actually published in Alma-Ata, which was then the capital of the Kazakh Republic, and that was in 1969. This book became very famous in the West, and here's a translation, an English translation published in 1976 in the UK, and I had a copy of this book, so I was very familiar with all of the results that had been obtained in Russia. And I was sufficiently intrigued by this work that in 1990, I went to Kazakhstan and met Professor Pezhnyakov. Unfortunately, he is now deceased, but this is a picture of me standing with Pezhnyakov in front of the Kazakh Academy of Sciences in Alma-Ata in Kazakhstan. This was in August 1990. And I'm told that the names on the buildings are both Kazakh and Russian languages. Work then started in Western countries, and in my own lab in California, we started working on superplastic materials, and we obtained a remarkable result. Using the lead tin eutectic, we obtained a record elongation of 4,850%. And here's a picture of the sample. This is the original sample. This is the sample after pulling to failure. And that result was quite amazing. And it was actually published in the Guinness Book of World Records in 1983. And in fact, it appeared in several of the books. This book came out every year. And it appeared in the book for about 8 years. Every year they included this result. But unfortunately, they then decided not to include these very obscure scientific results in their publication. And this was unfortunate because later, using the same material, we achieved an elongation of over 7,000%, which was a world record. and it was not included in the book because the book was no longer publishing scientific records. Instead, they started publishing records about movie stars and singers and sporting stars and things like that, but not scientific records. One way to achieve the small grain sizes that we need for superplasticity is to use severe plastic deformation, SPD. And there are different ways of doing this. And one way is high pressure torsion. High pressure torsion was actually introduced in the United States by Bridgman in the 1930s at Harvard. Again, it was not particularly picked up in America or in Western countries, but it was developed very extensively in Russia, and it's very effective for making nanostructured materials. And the other procedure that's used is equal channel angular pressing, ECAP. And this is truly a Russian procedure because it was developed by Siegel in what is now Belarus in the 1980s. And this is very effective for making sub-micrometer grain sizes. So looking at high pressure torsion then, what exactly do we mean? This is a picture of quasi-constrained HPT. And the basic idea is that you have a sample that typically is like a coin in your pocket. So it's like a disc. And here's the disc edge on. So we're looking at the edge of the disc. And it's placed between two massive anvils, which you can see here. We apply a pressure P, which is given by these arrows. Here's the upper anvil, here's the lower anvil. We rotate one of the anvils. Well, here we are rotating the lower anvil, and that gives torsional straining in the small disc. And it's called quasi-constrained because there's some extrusion or outflow of material, which you can see here, and that will occur during the process. So this is a very important processing procedure that is now used very widely, both in laboratories and in many applications. Now, if we look at the strain in HPT, the incremental shear strain is given by dl over h. So here is the rotation measured on the top of the disk. So here is a disk for HPT. dl is the displacement, as you can see here, and h is simply the height or the thickness of the disk. And dl over h is equal to rd theta over h. So here is the radius and the angular displacement d theta. The von Mises strain is then defined as 2 pi nr over h root 3, where n is the number of turns. And this means the strain varies across the disk. So it's a maximum at the outer edge, and it's a minimum, in fact, it's 0 at the center of the disk. Well, we knew about that. I was in touch with Alexey Zherebtsov, and we knew that there was this strain variation. And we talked about it, and we thought there should be an important effect on the hardness values across the disk. Nobody had ever looked at it at that time. No one had looked at hardness. So Alex obtained some samples, some HPT discs made out of high purity nickel, and he decided to deform these by HPT in Ufa, and he then sent them to me in California. And my student took measurements across 2 discs that he sent and measured the hardness. And here is the result. And this was the very first, I don't know how we get rid of this thing at the top, but in here it should say something about the first result that anyone achieved for hardness across a disc. And that was the work of Alexey Zherebtsov and our work, which we published in Scripta Materialia in 2001. And the important thing that you can see that nobody had seen before is that if we take a relatively low applied pressure, 1 gigapascal, we get lower values in the center and higher values at the edge. And if we go to a higher applied pressure, such as 9 gigapascals, which was the highest we could apply, so we get even higher values. And this result came out in 2001 and received 360 citations. Now, it was very obvious doing this that we should really make more detailed measurements and come up with an interpretation of what was happening in the material. And Alex made more samples using nickel and sent them to me. And then my student took many, many measurements of hardness across the discs. And Alex developed a way of making three-dimensional illustrations of the hardness distributions. And you can see that in these four pictures. These are pressures of 1, 3, 6, and 9 gigapascals. Each disk was taken through 5 turns, and we get variations in hardness across each disk. And we published this in a detailed report in Acta Materialia in 2003. And I noticed 2 weeks ago, this has now received 840 citations. So it's done very, very well in the scientific literature. A better way to look at this, instead of taking the colored illustrations that Alex made, an easier way is to look at these simple black and white drawings. This is the hardness if we have 1 gigapascal for 5 turns, and you can see that this is the disk. Around the edge, the hardness is higher, it's lower in the center, and this is true over a 3-dimensional configuration. And if we do the same thing, so this is for 1 gigapascal at 5 turns. If we change to 9 gigapascals at 5 turns, it's much more uniform. It still has a lower hardness in the center, but it's much more uniform than it was with the lower applied pressure. So this was work carried out with Alexey Zherebtsov in the very, very early stages, in fact, in 2003. And after that, of course, we participated in many other papers. So what I'd like to do then is to now explain some of the more recent results that we've obtained. If you process by HPT, generally the grain size is reduced and the material becomes stronger, but it also may become weaker. And there are examples of weakening, and the examples include zinc aluminum or lead tin. So you have to find out whether you have strengthening or weakening. And also the hardness that you achieve may not be stable over a long period of time. That means there may be a self-annealing effect. If you store at room temperature, the hardness may change. So we conducted experiments. I conducted these with my student Wang in Southampton. And the basic idea was to examine the nature of strengthening or weakening using the bismuth 42% tin eutectic alloy. We conducted all of the straining at room temperature. We went up to 10 turns and we used an applied pressure of 6 gigapascal. And the reason we selected this alloy was because this is the eutectic alloy, and it's very similar to the alloy used by Pearson. Actually, Pearson used the near eutectic bismuth 44% tin alloy. The eutectic is bismuth 42%. So Pearson's material was near eutectic, and that's when he obtained an elongation of 1950% in 1934. So it's essentially continuing the work that was first initiated by Pearson. Well, here's the initial results that we obtained. This is the microhardness values, the Vickers microhardness plotted against distance across the disk. It's a 10 millimeter disk. So this is an edge, and this is an edge, and here is the center. And you see immediately that we have a weakening. The as-cast material without HPT would be here, and after HPT, the values of the hardness are lower. So we do not get a strengthening in the bismuth tin eutectic alloy. And this is identical to results that we published earlier, both on, for example, zinc aluminum eutectoid and the lead tin eutectic. So you may think, well, if you take a two-phase alloy, maybe it will always show a weakening, but that's not true, because if you take aluminum copper, we've done a lot of work on aluminum copper eutectic, and this one shows a true strengthening. And the reason you get the weakening that you see here is because there is a breaking of precipitates during the HPT process. So these results are 6 gigapascals at room temperature with no storage. We took the disks, and within 1 or 2 hours, we measured the hardness. So it was almost instantaneous. And we have results for 1 turn, which is the upper one, and then 5 turns, and then 10 turns. If we store the material, the results change. So this shows an example of storing at room temperature for 14 days, and this produces a hardening. If we go back, you can see these are the results instantaneously after HPT, and this is the result after the storage, and these values are higher. So we now have a hardening effect. And what that tells us is that the microstructure that we produced in HPT is unstable. It is not stable, it changes with time. And we have a very easy recovery at room temperature. And this is due to a reprecipitation during the storage process. We can carry that further and do storage for a long period of time. This is the microhardness at a point 2 millimeters from the disk center, plotted against the number of days of storage. So we go from 0 days up to about 70 days on the right. And all samples we can see have a hardness of about 20 HV after storage for 20 days or more than 20 days. So the results for the 3 different numbers of turns are essentially coming together. And we get almost the same results here at about 20 HV. So this is not a stable microstructure. Here are the microstructures, in fact, and this is the one at the top left. The one in A is for the as-cast condition, and then we process by HPT for 10 turns and store at room temperature. And this is storage for 1 day, 7 days, 35 days, and the maximum that we did, which was 91 days. And you can see that the configuration is changing very, very visibly. And if we measure the grain size, we start off with 3.5 microns in the as-cast material. And then after HPT, it's reduced to about 0.94, but gradually the grains get bigger. And after 91 days of storage, it's about 1.81 microns. So the instability is very, very clear in these pictures. If we look at the superplastic properties, this is the as-cast material. So this is without HPT, testing at room temperature, the initial material, and this is 10 to the minus 2, 10 to the minus 3, 10 to the minus 4 per second. And you see these results are not superplastic. And if we do the same thing on the as-cast material at 363 K, again, we are not achieving superplasticity. So the material basically is not superplastic in the as-cast condition. However, if we deform by HPT and then store, this is stored for 35 days after 10 turns and testing at 298 K. So this is room temperature, this is 353 K. And you see we are now getting superplasticity. At room temperature, very nice superplasticity at the lowest strain rate, but at the highest strain rate, we have lost the superplastic effect. We do not achieve a 400% elongation. But if we go to the higher temperature, all of the conditions are superplastic. And at the fastest rate, we are getting an elongation of 1400%, almost 1500%. So now we have very, very good superplasticity. And we can understand that because if we plot the flow stress against strain rate for these conditions after aging for 35 days, this is at 298 K. So this is the room temperature result. 323 is here and 353 is here. You can see at 353 K, all of the points lie along a line that gives the strain rate sensitivity of about 0.5. In this case, about 0.54. But at room temperature, we have a superplastic effect at the lowest strain rates, but we lose this superplastic effect at the faster strain rate. And that's exactly what we saw in the samples pooled to failure. We had no superplasticity under these conditions, but we had superplasticity in this part at the lower strain rates. So the next thing we need to do is to ask, what is the mechanism of flow in this material? And to do that, we can look at some microstructures. I wonder why this little thing is in the way here. Can we move it? Maybe we can put it there. If you look at the microstructure, what we want to do is to understand the movement of grains. If we pull a sample to 1000%, it's impossible to study the movement of grains because they become separated from each other. So what we do instead, what we see here is 10 turns and storage for 35 days without tensile testing. That's here. And then 10 turns and storage for 35 days, and then pulling in tension to 30%, which you see here. Now, the first thing to notice is that the light grains are the bismuth rich. So these in here are bismuth, and the dark grains are the tin rich. So these darker ones are the tin. And we can see that there's a difference for the different types of boundaries. And if we look at the bismuth boundaries, we are opening up cavities and cracks. And let me give you an example. Let's look at grains 4 and 8. So here is 4 and here is 8. And here is the same place on the microstructure after pulling to 30%. And here is 4 and here is 8. And we've opened up a cavity between these two grains. And if we look also at grains 9 and 10, here is 9 and 10, here is 9 and 10, and we've opened a crack between these grains. And what we can find by looking at many boundaries is the grain boundary sliding is dominant on the bismuth boundaries. And we can do calculations which are given in the paper published in Acta Materialia. We can look at the diffusivities, and specifically the grain boundary diffusivities for the 3 types of interface. We have bismuth, tin, and bismuth tin. And by doing this, we can show that the maximum sliding on the bismuth boundaries is consistent with our calculations. So let me summarize then. Alexey Zherebtsov made tremendous contributions to our understanding both of superplasticity and of processing using severe plastic deformation. And I want to place emphasis on 2 of Alex's major accomplishments. He was the first to publish rigorous measurements of the hardness distributions across disks after HPT processing, using first of all 2-dimensional and secondly 3-dimensional representations. Nobody had done that until Alex's work, which we published in Scriptomet and Actomet. And he also co-authored with me the first detailed description of the fundamental characteristics of the HPT process. And these were very major important contributions from Alex. We then went on to look at recent experiments that we've conducted. Let's see if I can move this thing out of the way, get it up there, yeah. Recent experiments on HPT using a bismuth tin eutectic alloy. We showed that the alloy exhibits not a strengthening after HPT, but a weakening. due to a breakup of precipitates, but nevertheless, there is a subsequent straining if we leave at room temperature. In room temperature storage, we have a major sulfur annealing effect. Processing by HPT produces excellent superplasticity, and we have elongations in excess of 1,000%, and the strain rate sensitivity is close to 0.5, which is what we expect. So can I go on to the last slide? What happened to my last slide? I don't know what happened to my last slide. My last slide has disappeared, but anyway, it doesn't really matter because it just thanked everybody for, no, my computer's not working. Anyway, so that is the end of my talk. Thank you.
Professor Langdon, really thank you for such fundamental retrospective review through your experience with Professor Zhilyaev. As for me, as for young scientists, such information is really important. So, colleagues, we have about 5 minutes for discussion or questions. So you're welcome.
Can I ask?
Yes, of course.
Terry, nice to hear and to see you. This is Vladimir from Moscow. Terry, do you hear me?
Who is speaking, by the way? Put up your hand or something like that.
Hello. So my question.
Vladimir, it's Vladimir. Okay.
Yeah. It's me. My question to your presentation. Please explain us what's the what's the reason for different results between Pearson results and the last that you presented. So the elongation, it's very big difference. Only about 1,000% in the present results, and for Pearson it was more than 5%. It's about 5,000%. Please.
So the difference between which two things do you do? I didn't quite catch what you were asking actually.
So please again. So that you showed us that Pearson made some experiment and received elongation about 5,000% for material bismuth. And your presentation after high pressure torsion in the same materials you received the only not more than 1,000%. What's the reason?
Yeah, okay. So a very, very good question is Pearson 75 years ago achieved an elongation of almost 2,000%. We are now doing HPT, but we only have an elongation of just over 1,000%. Our elongation is lower.
Yeah.
But why is it lower? The answer is very simple. We are taking specimens cut from the HPT discs.
Yeah.
The HP discs are very small.
Yeah.
At the beginning, when we start the HPT, the thickness is 0.8 millimeters, 0.8 of a millimeter, less than a millimeter.
Yes.
After HPT, it is even smaller. We do not have enough grains in the specimen thickness to achieve these very high elongations. That is why when we look at the literature for HPT, the elongations are always lower than the elongations that you achieve using, for example, ECAP or more conventional techniques. The samples are too small. That is the problem.
Yeah, understandable. Now it's clear. Thank you.
Okay.
So, colleagues, we have about 1 minute for discussion. If somebody has a quick question, you're welcome. No? So, okay. Thank you once more for your report. So the next speaker is Professor Valiev from Ufa State Aviation Technical University, Russia. Professor Valiev, you're welcome.
Thank you very much, Dmitry. Can you hear me well?
Yes, everything is okay. We see your presentation.
Okay. 1 second. Now, I will be continue topic of bulk nanostructural materials produced by severe plastic deformation. But for broader auditory, special attention will be on innovation in this area for engineering and medicine. Now I represent two labs. One is Institute of Physics of Advanced Materials at Ufa State Aviation Technical University, and second, the Laboratory of Mechanics of Bulk Nanomaterials in St. Petersburg State University. Now, this conference is dedicated in memory of Alexey Zherebtsov, and I would like to say Alex, after graduation of Ufa Bashkir University, joined our laboratory at Institute for Metal Superplasticity Problems in the end of 80s last century, and it was very new laboratory and dealing with grain boundary studies and superplasticity, and also Institute for Metal Superplasticity Problems. It was just a new institute of Russian Academy of Science and founded by Professor Kaibyshev, who was the #1 Russian scientist in the field of superplasticity, and he was organizer and the founder of this famous institute. And my laboratory was also new, and Alex joined our laboratory, and he started also research on grain boundaries and superplasticity. And in 1992, he finished PhD thesis would be called candidate of science in physics and mathematics, and title of his thesis was study of relationship between the misorientation grains and texture of FCC polycrystals. From left side, you can see the cover of his thesis. Next picture demonstrates part of our staff of our laboratory, and you see several of these people participated in this conference. This is Alex Zhilyaev. Even after several years after this event, I was moving to Aviation Technical University, where we organized the Institute of Physics of Advanced Materials, but of course, we continued our close collaboration with Alex and and friendship, using many conferences, many talks, many meetings. Okay, in this talk, I would like to pay attention on some principle of producing bulk nanostructural materials from severe plastic deformation. Even Terry Langdon already considered several of them, but some main focus will be some principle of grain refinement and phase transformation induced by SPD processing. I will be trying to remind these important features, because they are responsive for nanostructuring of metallic materials subjected to severe plastic deformation, and I will be explain more precisely what means nanostructuring of metallic materials by severe plastic deformation. And of course, this is basis for nanostructural design of materials for advanced properties, including relatively new field multifunctional properties. And briefly, I will be consider innovation potential of bulk nanomaterials. And of course, many of this research were done with collaboration with Alexey Zherebtsov and my co-workers, and we will pay special attention on this. Okay, now for this broad auditory, I would like to start from illustration of different types of nanostructural materials. When we consider atomic clusters, nanoparticles, multi-layers, better to say nanostructural layers, nanostructural coatings, when coatings may be quite thick, but inside we can consider nanocrystalline structure. And for any application, structural application, many functional application is especially interesting field is bulk nanostructural materials. In this case, we can consider quite large piece of materials, it may be a centimeter now, and sometimes even several meters maybe, but inside they have very small grain size. For nanocrystalline materials, it's typically less than 100 nanometers. For ultrafine grain materials, we consider less than 1 micrometer, but from other hand, these materials may have many nanostructural features. I will pay special attention on this. Okay, and the focus of this presentation will be this kind of materials we call bulk nanostructural materials. Now, presently, there are two approaches to produce bulk nanostructural materials. One is bottom-up approach, is dealing with consolidation of individual nanoparticles or nanoclusters by compaction or consolidation of nanopowders processed by ball milling or electrodepositing. This is very famous approach, and a lot of publication from pioneer research by Professor Gleiter more than 25 years ago, 35 years ago. And but still, we typically can process relatively small samples with such ultrafine grain structure. That's why during last 2 decades, more and more attention was paid on top-down approach, dealing with grain refinement in bulk materials using shockwave loading and especially severe plastic deformation, which was started about 300 years ago. Now, there are several publications dealing with history of non-SPD materials. For example, one is Terry already mentioned about his paper in Acta Materiale with 25 years of ultrafine grain materials achieving exceptional properties through grain refinement. And second is relatively new paper, a review of high pressure torsion from 1995 to 1988. No, interesting, it is written by Professor Harita and Kavi Dalati and published 4 years ago. And this date, 1988, when we could process ultrafine grain materials using this approach. What this is a milestone of non-SPD materials. Already Terry mentioned about history of high pressure torsion through dealing with effects of high shearing stress combined with high hydrostatic pressure. However, only in 1988 we could demonstrate processing ultrafine grain materials through this approach. And regarding equal chain angular operation, it was started in 1989 through famous publication by Professor Segal and co-authors. However, only in 10 years later, it was first demonstration how possible to process ultrafine grain materials through this approach. Now, this picture illustrates first illustration of producing ultrafine grain materials by severe plastic deformation. When initial grain size, it was copper materials, could be decreased in 100 or 1,000 times in any section of this large billet. And very important feature, this is not a cell structure. This is really ultrafine grain structure having high angle grain boundaries, or mostly high angle grain boundaries. So this is indication of a real ultrafine grain structure. Now, at that time we had only transmission electron microscopy, and we showed through electron diffraction analysis, and especially effect of superplasticity was studied with these materials. It was demonstrated, also indication of high angle grain boundaries. Only later, this is from Terry and Alex publication in Progress Material Science, using already OIM or EBSD analysis was shown, yes, through severe plastic deformation, possible to process materials with mostly high angle grain boundaries, about 70 or even more % of high angle grain boundaries. So this was a further indication ability to produce ultrafine grain materials by severe plastic deformation. However, not only techniques, but now there are many techniques of severe plastic deformation, but also processing regimes important to produce ultrafine grain structure. Now we consider 5 main parameters. One, of course, a special temperature. It must be relatively low temperature, less than 0.4 from melting temperature. True strain must be very large, higher than conventional large plastic deformation, because only in this case we may have ultrafine grains with high angle grain boundaries. This is an important feature. And to reach such type of strains at low temperature, we must use hydrostatic pressure to enhance deformability, and also this is important for suppressing defect annihilation. And of course, vorticity and non-monotonic metal flow is important to produce, even after such huge deformation, it creates ultrafine grain structure. And simple shear methods, techniques like for high pressure torsion or equal chain angle pressing, they have a lot of vorticity mode. Materials, atomic structure, ordering and low stocking for energy also important to decrease grain size. What principle of severe plastic deformation produce ultrafine grain structure and also nanostructural materials will be published in 2002, and really it was first analytical review in this field. You can see a lot of citation of this publication demonstrating how broad and how broad and popular this topic presently. Okay, and in our book with Terry and Alex, bulk nanostructural materials, fundamental application, published more than 5 years ago, we considered not only grain refinement, but also some unusual phase transformation, very important for processing by severe plastic deformation. In some cases, we can consider morphization, nanocrystallization, dissolution of second phases, and especially for this presentation, important dynamic state engine, because in this case we can introduce grain boundary segregation and precipitation, and they're really unusual and not typical very often for metallic materials. No, few examples in this area. In early research with Yulia Kuzminova, we found complete dissolution of cementite after high pressure torsion of high carbon steel from left side. And in initial normalized state, this is mixture of cementite and ferrite, but after high pressure torsion, already at room temperature, complete dissolution of cementite, and we have quasi-martensite structure with grain size only 30-40 nanometers. So at room temperature, we can completely dissolved cementite. It was very unusual and first observation of such type of dissolution. As I mentioned, opposite, we may have very unusual aging phenomena, including dynamic strain aging. That was from recent publication where we used 3D atom probe tomography. We very carefully analyze situation at grain boundaries, and we found formation of segregation, unusual segregation, also precipitation, nanoclusters due to grain dynamic strain aging. And this is also a function of processing temperature. For example, after room temperature processing and at elevated temperature, very visible change of morphology of these defects. Therefore, we can introduce different kind of nanostructures in metallic materials using severe plastic deformation and also as function of processing regimes. Okay, more precisely, what kind of nanostructural features? No, of course, very important to look at grain boundaries, because when we have small grain sizes, we have a lot of high density of grain boundaries, and therefore we need to analyze what kind of grain boundaries we could process. And we need to consider low angle and high angle grain boundaries. As I mentioned, the goal of SPD processing, they produce ultrafine grains with high angle grain boundaries mostly. No, but fraction of low angle grain boundaries, it might be also quite high depending from processing regime. Special and random grain boundaries. No kind of special grain boundaries is twin boundaries. For example, in some materials like stainless steel, we can, or even titanium materials, so we can introduce quite a lot of special grain boundaries, twin boundaries in matrix by severe plastic deformation. Important feature also for even we have high-end grain boundaries, they may have equilibrium character or non-equilibrium character. And a relatively new area of research in this field is grain boundary segregation and precipitation, and I will be paid in my presentation on these features because they very strongly may affect on properties of materials. Okay, few examples of what means non-equilibrium grain boundaries. Already in Yulia, our researcher of SPD process materials, we could observe very specific grain boundary structure. No, for example, this ultrafine grain in aluminum magnesium alloys, and these two regions with atomic resolution, and even with magnification to nanometers only, and this is atomic place. And you can see, even if we have high angle grain boundaries, we may have a lot of features. This is steps, facets, and very often we could observe dislocation, and in further studies we also analyze disclination structure in grain boundaries. All their illustration of non-equilibrium grain boundaries, which concept was introduced in 90s, and we could say, in contrast to equilibrium grain boundaries, non-equilibrium grain boundaries, they have for the same misorientation parameter, theta, they have enhanced free volume, enhanced energy, this grain boundary, and long range stresses to compare with perfect equilibrium grain boundary. The origin of such features associated with extrinsic grain boundary dislocation. So this is very typical feature of many materials processed by severe plastic deformation, and from other hand, it may have also effect on many properties. Now, more precisely about grain boundaries and their segregation. First observation was done in publication with Xavier Savage and our students were using 3D atom probe analysis to be found in, even though we have very small grain size, about 100 nanometers, a lot of grain boundaries, they have many features, and including segregation of, in this case, magnesium, copper, silicon, and all these segregations situated mostly at grain boundaries. So it was first observation of this, and later it was very clear evidence. All segregation, all alloying element may be segregated mostly at grain boundaries, like you can see here after severe plastic deformation in traploid or at grain boundary. And morphology of this segregation we analyzed in several publications. Quantitatively, amount of this segregation, they have enhanced concentration of elements and also crystallographic and the width of this segregation zone very often is visibly larger than crystallographic width of grain boundary. So this is kind of near grain boundary zone with enhanced concentration of alloying element. And later it was shown this is very typical for many materials, for example, aluminum alloy, stainless steels, and amount of this segregation phenomenon is function also for processing regimes. For example, this is processing at elevated temperature, and for processing at room temperature may have a visible difference in concentration of alloy elements. Okay, so through severe plastic deformation, there is ability to produce different kind of nanostructural features. It's not only small grain size, it's control of grain boundaries, precipitation, nanoclusters, and so on. So in function of processing regimes. So we need to make nanocharacterization of these features using advanced methods like 3D atom probe, high resolution microscopy, and so on. Why is it important? Because they are responsive for realization of transport mechanism, diffusivity, deformation like grain boundary sliding. It's a function, direct function of processes at grain boundaries. And therefore, through control of transport mechanism, we can control mechanical and functional properties, and even introduce multifunctional properties, which are really interesting and important for performance of advanced materials. This principle will be described in our book, Terry already mentioned. Okay. What is recent our studies, what kind of really multifunctional properties possible to produce through nanostructural design by SPD processing? Now, several of them, they're really unique combination of, for example, super strength and ductility of materials, which are really important for structural application. Increased strength and electrical conductivity. Well, what is here is important, because strength and the electrical conductivity is typically trade-off properties, because when we can increase strength, typically will be decrease electric conductivity. However, very important for any practical application, for fundamental study, how we can find ways to approaches to increase both strength and electric conductivity at the same time. This is important task for development of advanced conductors. The same for increased strength and corrosion. Typically, when we make stronger materials, corrosion resistance is less, or radiation resistant. But how we can increase? And this is topic of very important topic for biomedical applications. For biomedical application, because in this case we need to have combined advanced mechanical properties, advanced biomedical properties for processing, for example, new kind of medical implants. no, short examples how we can decide such type of important problems through nanostructuring. No, this is from Yulia, our research about how we can increase strength materials because many studies show that when we have smaller and smaller grain size, we at first we can increase strength, but finally for the smallest grain size, typically we have negative hole patch relationship. However, from fundamental point of view and especially practical, it's important to have enhanced strength, to have positive hole patch relationship. How we can reach this? And this idea was proposed by Professor Firstov from Kiev, where they analyzed nanocrystalline chromium containing some segregation grain boundaries and showed, oh, in this case, we can combine this strengthening mechanism. We proposed and later we made several research in this field. We can combine several strengthening mechanisms. This is not only grain size hardening according to this whole patch relationship. This is precipitation hardening. If we can introduce a lot of precipitation in nanoclusters, solid solution hardening, dislocation hardening, depending from again processing route. And also important new kind of mechanism we call grain boundary hardening, which is associated with grain boundary segregation. It's also important feature in some cases may introduce very essential additional strain hardening. No, several experimental research were done to demonstrate this phenomenon. For example, with aluminum alloys. What typically during many years, development of aluminum alloys allowed to increase yield strength of conventional aluminum alloys from 200 megapascal to up to 600. However, through nanostructuring, where we can combine several strengthening mechanisms, it was possible to get 1000 megapascal strength and sufficient ductility, which much higher than traditional hardening of these materials. This is, in this case, materials already, aluminum materials, they have strength even higher than many steels. No, similar research with Nariman in Kiev, Marina Abramova were done on austenitic stainless steels, where also not only grain size, very important to have grain boundary segregation, precipitation, because in this combination we may have additional hardening about 500 megapascals. So we have several publications in this field. Okay, but not only strengthening, combination strength and ductility is important. We know from earlier publication of Professor Tsuji group, when we have smaller grain size, yes, we have higher and higher strength, but ductility might be visibly less, and especially when you form elongation, you can compare initial state and with smallest grain size. And this is quite typical for ultrafine grain material. So how possible to decide this problem? And 2 years ago, we published a paper, and I discussed at the time with Alexey Zherebtsov many things in this field about mechanism of ductility in ultrafine grain materials. And from mechanical point of view, we need to consider criteria, hard criteria, and due to this, controlling of strain hardening parameters, strain rate sensitivity, in many cases possible to combine strength and ductility together. This is important field. And regarding grain boundaries, we can really realize superplasticity in not only at low temperatures and high strain rates, and ultra low temperatures, because we can control not only grain size, we can control through grain variation of grain boundary structure diffusion and grain boundary sliding, and in some cases we can realize in conventional alloys like aluminum alloys, magnesium alloys, superplasticity already at room temperature. This is very unusual phenomena, and this is associated with control of grain boundaries and their segregation. And you can see several publications with Professor Harita group. Okay, and we analyzed the state of grain boundaries and segregation, and found very essential effect of grain boundary segregation on superplastic behavior. And a few words about combination of high strength and conductivity. In this case, also research of nanostructural features where we can combine not only small grain size, we can combine precipitation and segregation inside. In this case, we can develop materials having both combination of high strength and conductivity through control of a solid solution in this case also. And this is really exciting field because in this case we may have very high hardness, strength and conductivity to much higher than conventional processing routes for aluminum alloys and for copper-based alloys. And future overhead power lines, there are many chances we will have nanostructural structure with such combination of nanostructural features and enhanced volume. And Georgy Raab could not present a special talk, but it will be later because in close collaboration with him, several recent modification of ECAP processing was developed, ECAP conform, ECAP with parallel channels for processing different materials, and presently we could use for biomedical materials, for example, for titanium, where through variation small grain sizes possible to produce very high strength and enhanced fatigue strength, and therefore this is a way for miniaturization of medical implants. No, for example, this example of dental implants produced our colleagues, Professor Ludwig Luchasz from Czech Republic, and from using nanostructural titanium. And another, this is also collaboration with medical people processing screws, plates from nanostructural materials with advanced mechanical properties, and also it was found improvement of biomedical properties. And another interesting field is demonstrated by Professor Yulia Astanin in miniaturization of devices using nanostructural materials. Okay, and before end, I would like to demonstrate recent modification of ECAP pressing for innovative application using multi-ECAP conform with developing our laboratory acting prototype, and now implementation of this technology to development and installation of special die set at our Nanomet startup company. No, about these achievements we will be discussing in further presentation. Okay. No, first of all, I would like to say nanostructure of metals is really can increase level of properties, and this will approach for development of multifunctional properties for various applications, and ECAP conform can be successfully applied in many cases for this aim. And finally, again, I would like to thank organizers for inviting to present this talk, and of course Alexey Korchunov for many years our collaboration and friendship. Thank you very much for your attention.
Thank you, Professor Valiev, for such fundamental report. And as usually from position of young scientists. Thank you for such motivating story of beginning of such great scientist as Professor Zhilyaev, because he finished his PhD thesis when I was 2 years old. So, colleagues, we have about 6 minutes for discussion and questions. You're welcome.
May I ask one question?
Yes, of course.
Dear Ruslan, it's glad to see you and to hear you, of course. And, my question concerning the problem of thermostability. So it seems you did not mention about it. What can you see? What can you tell about it? What's the direction for this problem?
No, of course, this is very famous and important problem. Of course, very often ultrafine grain materials, they have a low thermostability because high driving force for grain growth. However, when we can control grain boundary structure, especially through grain boundary segregation, and I would like to pay attention, grain boundary segregation is quite broad topic, a lot of different kinds of segregation. We can say now one kind of may lead to enhanced diffusivity, and other kind of segregation in opposite will be decrease diffusivity in growing growth. And presently there are quite many examples enhanced thermostability. For example, there are some examples when we have stable ultrafine grain structure up to 0.8 from melting temperature. So this is important topic, and during last years there is interesting example of how we can decide.
Okay, thank you.
Colleagues, do you have any questions? So thank you. Thank you for report. The first part, the first part of our event is finished now. According to schedule, we finished plenary session, and now we are going to section with reports. Unfortunately, I don't see Professor Tandon in list of participants in our Zoom conference. But anyway, I have his pre-recorded presentation. I think one moment.
Hello, good morning, good afternoon, good evening, in whatever part of the world you are. My name is Puneet Tandon, and I'm going to make a presentation for the 5th Magnitogorsk Materials Week conference to be held from April 5 to 7, 2021, in the fond memory of Professor Zhilyaev. The title of my presentation is Hybrid Manufacturing, and I hope my screen is visible to you, all of you. I'll begin my presentation by making an obituary to Professor Zhilyaev. In fact, just before the lockdown occurred last year, my visit to Russia was scheduled in the same days, and I was going to meet Professor Zhilyaev at Ufa. But probably that was not a part of the destiny. I miss him, and I very fondly remember him not only as a great learned scholar, but a very fine gentleman. Okay, coming back to the conference, this is my institute, which is located at the city of Jabalpur in the central part of India. And this way you can fly from Magnitogorsk. What I'm going to make presentation today is, apart from introducing the topic hybrid manufacturing, I'll be talking about a few topics. Hybrid manufacturing is a broad topic, so I just want to confine myself to a limited topic given the time given by the organizers of the conference. So I'll be briefly touching upon additive subtractive manufacturing process. I'll talk about ultrasonic vibration assisted incremental sheet forming, which we call as UVAISF, incremental stretch drawing, and deformation machining. Now, all these processes, which I'm going to show you, will have some results, some photographs from the work done by my group and work which is funded by various sponsoring agencies. So to begin with, I must thank the members of my team, my colleagues, my students, my collaborators, and the funding agencies. So what is hybrid manufacturing? So as per the SERB definition, hybrid manufacturing processes are based on the simultaneous and controlled interaction of process mechanism and or energy sources or tools. So basically it can be when two or more than two manufacturing processes, their process mechanisms are having a simultaneous effect, simultaneous and controlled. The energy sources are simultaneously utilized or the tools are simultaneously utilized and which are making a significant improvement in the performance, process performance. Now, please understand that hybrid manufacturing process are not what we call as combined manufacturing processes. So if we are following drilling after milling, or if we are following heat treatment after milling, they are not simultaneous. So they are not hybrid manufacturing processes. On the other hand, if we are combining, for example, simplest example, electrical discharge machining, electrochemical machining, what we call as EDCM, that is probably a hybrid manufacturing processes. So this is a schematic representation. So hybrid manufacturing processes can be broadly classified in two categories. Number one, where we are combining different tools or energy sources, or number two, where we have controlled application of process mechanisms. The combination of different tools and energy sources can be further classified into two different processes, what we call as mixed processes and assisted processes. So what happens? Let me explain to you with some of the examples. So examples of mixed hybrid processes are, for example, additive subtractive manufacturing process, curve profile extrusion, electrical discharge machining, electrochemical machining. Now in this slide and subsequent two slides, the processes which I have colored with red are the processes which I'm going to talk about in this presentation. So examples of assisted hybrid processes include ultrasonic vibration assisted incremental forming process, laser assisted turning, vibration assisted grinding, vibration assisted electrical discharge machining, media assisted cutting, laser assisted bending. And examples of controlled application hybrid manufacturing processes include incremental stress drawing, deformation machining, which is a combination of machining and incremental sheet forming. And you can see this is the upcoming field. So I'll be talking about both the process in detail. So let us begin with additive subtractive manufacturing process. So this is an example where we are using a conventional 3-axis CNC machine for depositing polymer and doing milling or machining on this part, fabricated part, so that we get the near net shape manufacturing. So we have a deposition system, we have a heater, so that the polymer are liquefied and they are printed, and then they are simultaneously being machined. So these are some of the examples of the samples being produced. Moving ahead, we'll talk about ultrasonic vibration assisted incremental sheet forming, UVAISF. So which is a combination of ultrasonic vibration and incremental sheet forming. I hope everybody is aware about the incremental sheet forming process, where we are going for a controlled forming of a sheet in an incremental manner. So the process starts with the CAD model of the geometry which we want to fabricate. From the CAD model, we generate the tool path. That tool path is fed to the sheet on either a CNC machine or a dedicated machine. And when it moves in tool path circumference, it is forming the geometry which is there in the CAD model. Now that particular process, if we have a combined ultrasonic vibrations of the tool which is moving and vibrating, that's what we call as ultrasonic vibration assisted incremental sheet forming. It is something like this. So you have a tool which is forming a sheet which was initially straight, and it is also vibrating. So you can see this ultrasonic transducer which is vibrating a forming tool at ultrasonic frequency. And in the process, it is forming the geometry. Obviously, this process offers a lot of advantages. So that's why it is a preferred process. So this is the schematic of uh, different parts, what we have in the case. So in the case of ultrasonic vibration, we have ultrasonic vibration transmission system. So this is a piezoelectric transducer, which is giving vibrations on the tool tip. So here we attach the tool, this is a tool holder. And this we have a frequency measuring instrument where we can find out what is the frequency of vibration. This is a machine which we have designed and developed in-house. This is an 8-axis machine. So we have 4 axes at the top, X, Y, Z, and spindle RPM, and 4 axes at the bottom, X, Y, Z, and the spindle RPM. So this machine is basically a double-sided incremental machine. So on this machine, we can remove one of the axis and we can attach an ultrasonic vibrator to provide ultrasonic vibration at this. I'll show you some example. This is another view of the DISF machine which we have in-house. This is a second machine. Interestingly, this machine is a vertical machine where the tools are vertically aligned and the sheet is placed horizontally. And this machine has a table size of 350 cross 350 cross 250 mm. This machine is a 10-axis machine where we have where the machine is horizontal. You can see this is the spindle, and there's another spindle also horizontal. The sheet is placed vertically. So this is a fixture, and we have sub fixture in this fixture so that if we want to put a smaller sample, we can put it to it. And both these machines are funded by some of the sponsor agencies. So you have X, Y, Z, and spindle RPM 4 axes on this side, and this side X, Y, Z, spindle RPM, along with the tilt and roll and yaw is also given, so that we can form inclined geometries also. So that makes a 10-axis machine. Again, as I told you, designed and developed by us in our laboratory, fabricated by some private consultant. So this is another view of the same machine. So you can see this is the roll and yaw, which is you can provide on this side. And this is like you have 4-axis machine. Now this head can be removed and we can put a ultrasonic vibrator on this side to have ultrasonic vibration. These are like some of the process mechanism and samples. You can see this is some adaptation which we have done. This is an ultrasonic vibrator tool which is vibrating. You can see the connected, and this is the snapshot of the vibrating tool and with the coolant, because a lot of heat is being generated. This is another variant of DSF process where we are using heat, localized heating of the sample. And this is what we call as elevated temperature incremental sheet forming. And we are measuring the temperature and we are measuring the geometry also through this particular process. I can show you one example and that will make the picture clear. So this is a DSIF forming process. Just enjoy the video. You can see a different geometries being formed, complicated in touch with the holders. And when we press it, the sheet will move in. So this much is the leverage for the drawing operation, as you can see in this example. When you press this and there is no control, unlike a conventional drawing operation where you have die and punch, here we have only a punch. So this may go up. So that's why we require multiple operation. In the second case, this aberration will be taken care of by using a medium-sized tool and moving inside out. This is a tool which is moving inside out, and you can see it is developing the geometry as per the desire. And finally, we use a smallest size tool, the tool path of outside in, and we generate the desired geometry as is evident from this particular image. So the example, we can have some non-symmetric shapes also. And if you compare the conventional ISF process and the incremental sheet drawing process, incremental stretch drawing process, you can see the forming depth is significantly larger. Here the crack appears, and in this case, in the ISD process, there is no crack even after a larger depth also. So the advantages being offered by incremental stretch drawing process, this also leads to better material flow. It can control the wrinkling of the sheets, the thinning, which is one of the major defect or challenges in the incremental sheet forming process. That is taken care in this particular process. And then this leads to better formality than the conventional ISF process. The last process which I'm going to talk about today is again a hybrid process. which is combining machining and incremental sheet forming, and we call it deformation machining. So we have a thin structure machining followed by the ISF process and leads to deformation machining. Now, the advantage of this particular process is that we can make complex monolithic parts also. That means we can avoid assemblies, joinings. So particularly if you have a component which is working at high speed, high RPM, or high temperature, something like a turbine blade, and you have a welding, or if you have a joint, or if you have an assembly, that becomes the weakest point. So we'll make a monolithic component by this particular process, and that will avoid any such error in this case. This is the schematic representation. Deformation machining is also of two types. One is the bending mode and second is stretching mode. So when we start with the process, we have a block of this size and we do machining and make a thin wall like this. So from a block of maybe H plus H1 size into L and width of this, we machine the two sides and we make a wall. So this wall, then the hemispherical tool is replaced by a punch, and we gradually move the tool path like this, starting from here, and it keeps on bending. So this is called as bending mode. You can see. So we on a block we are able to make a bent component, and this is what you call as a deformation machining bending mode process. The second is stretching, where we make again from a cuboid we make a hole with a thin bottom surface, thin floor, and then this cutting tool, milling tool is replaced by a forming tool, and we move in this and we convert this floor into a conical shape. So this is what we call as a deformation machining stretching mode. You can see again, so this is the actual process. You can see spindle, the fins being made, and then you are bending the fins as per the desired geometry. And you can see these are all of different angles. So I can control this with the tool path, which is generated from the CAD model of the component to be generated. This is a bending mode, and you can see this is a cavity, and you have a thin floor, and this thin floor is converted to conical component, what we call as a stretching mode deformation machining. And this is an actual example with a tool path. So again, this is a tool which is converting a monolithic component into a bending mode, and this leads to what we call as a bending mode deformation machining. This process, as I mentioned, we can produce monolithic geometries, even of complex shapes. This can provide better control over the properties of the formed components. We are able to reduce the weight and cost in the components in comparison to the conventional processes. And material wastage can be also controlled. We can have a controlled thinning in the walls, and it can lead to better formality than the conventional ISF process. So that's all from my side. Thank you. These are my contact details. Anybody has any question, you may feel free to drop any mail or text over there. I'll be more than happy to reply it. Once again, thank you for being patiently listening to me, and have a nice day ahead. Thank you very much.
Thank you, Professor Tandon, for your presentation. I think he will see us in recording on YouTube, but unfortunately without his video, because this part was blocked by author rights. So next report will be from Petr Zhilyaev, Skolkovo Institute of Science and Technology, Russia. Petr, you're welcome.
Okay. Good day, everyone. First of all, I want to thank everyone to participate in this conference in memory of my father. I won't show any pictures of him because this is too hard for me, but nevertheless, I'm very pleased that you have participated at this conference. Today, I want to talk about atomistic modeling of grain boundaries migration in nickel. This work was highly motivated by my father. Actually, previously I was not really involved in ultrafine grain structure materials, and this is kind of our first attempt to apply molecular dynamics to study this kind of interesting type of materials. Yes, first of all, a few words about motivation. As from the first brilliant presentation by main persons in the field, you know that mechanical properties significantly depend on microstructure. And it's very interesting that changing only microstructure alone can significantly alter mechanical and even biomechanical properties. And here's some example. This picture we already see by Professor Valiev, when changing nanostructure actually increase properties of the material in both directions that really was unpredictable. Another example is also the work, which one of the co-author was my father, Professor Zhilyaev, where they show that changing the microstructure of the material also increase the ability, the ability of cells to grow on them. And another example is also the work that quoted my father from Nature, when they got low temperature superplasticity again, just changing the microstructure of the material. But still, there are many questions and many problems for the ultrafine grain structure of ultrafine grain structure materials. One of them is the control of grain boundaries. Everyone know that a lot of effort is pushed to increase the thermal stability of grain boundaries. So you can produce such kind of materials with very, very tiny grains, but eventually they will grow and it will deteriorate the mechanical properties of such materials. And so a lot of efforts are pushed to stabilize this kind of growth. And actually, this growth is described by a so-called Arrhenius equation, where D is the average grain size, the T is time, T0 is some kind of constant, and EA is the activation energy of grain growth. And so this kind of very important quantity, and to predict the grain size grow in ultrafine grain materials. And the problem is that this kind of very important feature of grain materials is there is a big mismatch between real experimental values and values obtained in theories such as molecular dynamics simulation. So, and here you can see the example of grain growth during the time for different temperatures. So we decided to investigate the activation energy of grain boundary migration by means of molecular dynamics. So this is a theoretical method. It is an atomistic method, so each atom is considered explicitly. And the main idea of this method is to apply Newtonian equation of motion to get the acceleration. And if you know acceleration, you can get the velocities. And if you know the velocities, you can get the next coordinates or atoms. And so that's how your system is propagating in time. And the main component of the molecular dynamics simulation is the notion of the atomic interpotential. So it's the crucial part, how your particles, atoms, interact with each other to calculate the forces that are acting on them. In this work, actually, we use embedded atom method. It's pretty popular method for metallic system, and the energy part consisting of the embedding function and pair potential. Okay, and just again a few words of molecular dynamic simulation. What is it? Here is like a simple example of molecular dynamic simulation. It's the deposition of copper atom on a coal substrate. And as I said, initially you set some position and velocities of your system. So this is the initial condition. Then you predict the position of your atoms because you know the velocity and you know the acceleration. You also update the velocities. After that, you get the second step of the position. You calculate the force, and after the calculation of force, you again know the acceleration, and you propagate your system n times. And after that, you can calculate every physical properties of the interest that depends of the atomic structure of your system. So this is so. So to calculate the migration energy of grain boundary in nickel, we actually use 4 different methods. The first method will be the flat boundary driving force, the flat boundary fluctuation model. We also use nucleation model, and I should say some kind of natural model that we call polycrystalline model. The first model that we used to calculate activation energy of grain boundaries was a flat boundary driving force model. So we consider a big crystal and the grain boundary between these parts of the big crystal monocrystal. So these 2 crystals, they are orientated differently. And so the small amount of atoms that are making a grain boundary between these these monocrystal. We also apply a small shear on the system, and because of this strain, the grain boundary began to move. And we can calculate the position of this boundary in time. And from this dependence, we can calculate in a pretty simple way the velocity of this boundary. So here you can see the change of the boundary position in time for different time, different temperatures. So the higher temperature is it, the faster the boundary is moving. So from this curve, we can calculate the velocity of our boundary. And because we know this velocity for different temperature, we can calculate the dependence of velocity on temperature. And assuming the Arrhenius behavior of this dependence, we can calculate the activation energy. We also check different values of strain and show that the activation energy is strain independent, and we calculate the activation energy, which was half of electron volt. Okay, so the second method was also consider a flat boundary, but this time we does not apply any strain on our system. We was just monitoring the fluctuation of the grain boundary in time for a long time. So if you watch very closely to the position of the ground boundary, it will, in some sense, like breathing in some sense, so changing its position slightly. And we can calculate the dispersion of this position, and it is known that this dispersion is connected with the mobility of grain boundary. So, and again, we calculate the dispersion of the grain boundary for different temperatures. And again, the higher temperature is it, the greater dispersion you have in time. And from the dependence of the mobility on temperature, we assuming the Arrhenius formula, we again can calculate the activation energy of grain boundary, and we again get a value close to the half of electron volt. So we show that these two methods with some kind of the same model system give approximately the same results. So another other attempt, the third model that we use for calculating the activation energy of the grain boundaries by means of molecular dynamics was a so-called nucleation model. So here we take some spherical precipitate inside ideal structure and move it on some angle and relax the system. Because these two types of monocrystal have different rotation, a spherical grain boundary appear, and if we give this system possibility to evolve in time, we saw that this nucleus, it shrink or it grow. In this case, it was shown that it is shrinking, and the velocity of this shrinkage is also dependent on temperature, and this velocity is also governed by the activation energy of grain boundary migration. And again, we calculate the dependence of radius on time for different temperatures, and we calculate the velocities for this temperature, and assuming the Arrhenius dependence, we evaluate the activation energy of grain boundaries for another type of the system. And in this case, we get considerably smaller amount of activation energy, like 0.1 electron volts. Yes, so it's not very good for predicting activation energy. That different methods give different results. So to be more close to the real system that we have in real experiments, we consider the fourth model to calculate the activation energy. This model is more natural because we consider a polycrystalline sample of the polycrystal. So we create this kind of polycrystal with the Voronoi method, and we evolve this crystal in time and monitor the size of the grain boundaries in time for different temperatures. So noted that unfortunately the molecular dynamic simulation, it doesn't allow to model the full size crystal. So the grain size of this crystal is pretty small. It's about 2 nanometers. So it's a little bit far away from the smallest grain size that we have in experiments. So in some sense, this is ultra fine grain, ultra fine grain size polycrystal model. So the problem of this model was that it's very hard to calculate the evolution of the grain size in time by your hands, because you have different grains in different orientation. So for that purpose, we develop our own algorithm who automatically calculate the grain size distribution for these 2D crystals. So we make like a lot of slices, 2D slices, and our algorithm analyzed these slices. We found, here you see kind of EBSD style coloring picture. And from this picture, you can evaluate the grain size, approximated it by a sphere. So this is more like a natural method. So we calculate the grain size radius for 3 different slices, like that was involving in time for 4 different temperatures. And again, so this is grain slice that are growing. And so from this dependence, we calculate the velocity of the grain size changing. And from the velocity dependence on temperature, we calculate the activation energy. And we get, on average, like 0.57 electron volts. So amount that is higher than we get for the flat boundary case. Here is the conclusion. So again, this is the values of migration energy that we get for 4 different methods. And unfortunately, yeah, this is still there are a lot of place for research here. Still, we are not even close to the experimental value of migration energy for nickel. So the changes drastically, and still this is a problem that even for, how to say, very natural model of polycrystal, we get very low migration energy. And in experiments, we have about 1.5 electron volts. It depends on a lot of factors, but unfortunately, our studies show that still molecular dynamics cannot get the right type of migration energy. And this is also means that we cannot propose a mechanism of the migration energy, true mechanism, because we can not get qualitative results in comparison with experiments. And hence more investigation are needed. As I said, the more large sizes system should be considered, because our grains are pretty small, so we should enhance them in a 5 times, I think, to be like even a little bit close to experiments. Another interesting things is that it is known that interstitial atoms at the grain boundaries, even very, very small amount of them, can drastically change the activation energy. And so, but in molecular dynamics, we consider like pure substance. And in this sense, of course, we also should include them to calculate the influence on the migration energy. But for pure system and for small boundaries, we have kind of very small migration energies in comparison with experiments. I think I finished my presentation. Thank you for your attention.
Thank you, Petr, for your presentation. Time is out, but anyway, if somebody has rather fast, short question, you can ask. Maybe we can make 2 minutes, for example, for this.
May I ask the question, please?
Yes.
Petr, thank you very much for a very interesting presentation. What will be changed in the model if you will take another object for investigation, not nickel, but for example, copper or aluminum?
Actually, not much. only interatomic potential should be changed. And also, if we consider flat boundary model, you should change the orientation, because we take some in average of orientation that experimentalists see in nickel, because the orientation of grain boundaries is actually very, very important. And to be precise, you should calculate all type of orientation, average, or the distribution of the orientation that you have in the experimental sample. But here is just kind of an average case.
Thank you. And one more question, please. And what kind of experiment it is necessary to carry out in order to prove the accuracy of the model?
I think it's not the problem of the experiments, it's a problem of ours. So you should take a larger system. I mean, here we have about 2 and 4 million atoms, and I think the good size for system to make a right comparison of experiment should be about billion atoms. So you should pay a lot for a computational power for that. And also you should include some interstitial atoms, and this is kind of also the problem. So, and then you can compare it with the experiments that exists. Yes, yeah, that's.
Thank you.
So, colleagues, thank you. The next reporter is Evgeny Naydenkin from Institute of Strength Physics and Material Science.
I think you're wrong. That's the next presentation is Vladimir Stolyarov.
Sorry.
You're
Yes,
right.
of course. Vladimir Stolyarov from Mechanical Engineering Research Institute. You're welcome.
Before start my presentation, I would like to say a few words in memory of Dr. Zhilyaev. Dear conference participants, for many of us, the news of Alexander Zhilyaev past was shocking and caused deep sadness. I happened to work with him for about 20 years, and I can say that he was a good man, a good friend, and wonderful scientist. I will always remember him as a cheerful person. So it's very sad that he is absent now. So I will start my presentation. My presentation will prepare 2 organizations. First, Mechanical Engineering Research Institute of Russian Academy of Science, and the second is my partner Irene Kalyari from University of Padua. So there you see the title. This is, I will tell you some information about interaction of plastic deformation and pulse current for different metals. So the content, you can see motivation, materials, methods, and several features. This is main issues for my presentation. It will concern abnormal electroplastic effect and effect in amorphous in nanocrystalline states, and strengthening by current instead of softening, and structure refinement by electroplastic effect. Motivation. So you can see several points that connected with motivation. The first is a typical electroplastic effect looks like downward stress jumps. Does it always? The second point is, does the structure state amorphous, crystalline, nanocrystalline, and doesn't matter, effect on the electroplastic manifestation? And the second point, the third point is we should understand what's the difference between Joule and electroplastic effect, because both effect influence on the mechanical behavior. We need to separate both effects. The next point is very important. What's the role of Martensite transformation induced by strain on temperature? Because there are many materials who has transformation. Is it influence on the on electroplastic effect? The next point is, does current always leads to softening? Because maybe sometimes it's possible strengthening. And finally, is very important to consider possibility of electroplastic application for metals during working technology or nanomaterial processing. So the total goal is to demonstrate some unusual features of electroplastic effect that was not indicated in literature. About materials and methods, we used several pure metals like titanium, aluminum, and also the complicated alloys like iron, silicium, boron in different structure state, and titanium, nickel, shape memory alloys, and duplex stainless steel. The structure state was changed from coarse grain to ultra-fine grain, from nanocrystalline to amorphous, and why it is necessary to have a look on these features. For example, for titanium nickel alloy, we have on the stress strain curve plateau that responsible for martensitic transformation from austenite to martensite. It's interesting to understand what kind of electroplastic effect we can observe on this stage. Materials like duplex stainless steel is interesting because this is two-phase materials, and we know that different grain boundaries can also influence on the electroplastic effect. So we used tension test and such samples. It's a big sample, so it allow us to process a good tension and to receive a good characteristics. So that from this slide you can see different mode and different regimes of current. So we vary current from single pulses, multi-pulse current to direct current. We also changed current density and pulse duration from 1 to 1000 microsecond, and current density from several tens to several thousand ampere per millimeter square. We also used the multi-pulse current with a little bit less current density, and for direct current, we also used very small current density because of some thermal effect. So here you can see the first features for electroplastic effect. This is typical electroplastic effect. You can see downward stress jumps. But if we consider another materials like materials with martensitic transformation, we see that there are different kind of electroplastic effect. First, we see the stress jump up and another stress jump down. If we change alloys, from this to equiatomic titanium nickel alloy, we see that sequences of the effect will change from electroplastic effect to shape memory effect. So this is the first features that we can observe, not only typical electroplastic effect, but also shape memory effect in these materials. The second feature is on this figure you can see stress strain curve for amorphous state materials and after some crystallization. This is iron silicium boron. It's processed by melt spoon technique, and in initial state the material is in amorphous state, but after annealing about 700 degrees centigrade during the 10 millisecond, we can observe electroplastic effect. So we can support idea that electroplastic effect we can observe if there is a mechanism of electronic wind, I mean dislocation moving. The next feature is strengthening by current that we observe. That we observed in titanium and aluminium. So the titanium was polycrystal and aluminium was single crystal. We see that single current pulses, in contrast to multipulse or direct current, are capable causing the strengthening and increasing plasticity. Really, the curve number 2, we see strengthening and a larger plasticity in comparison with without current curve and for multipulse curve and for direct current also. The same situation for monocrystal. So this effect is total for polycrystal or single crystal. The hardening effect is greater the number of current pulses, and perhaps the strengthening can be caused by cross slip of dislocation or thinning. So it's necessary to have additional experiment. This is next features that show us that it's possible to use electroplastic rolling. It means rolling with a multipulse current. We can to refine microstructure at the grain size will depend on the post-deformation annealing temperature. For example, for 400 degrees annealing, we have grain size less than 50 nanometers. If temperature more, we have grain size more than 100 nanometers. So the electroplastic rolling makes it possible to increase the accumulated grain degree more than 1 without fracture, and thus obtain nanocrystalline structure and hence fractional properties after additional annealing. It's seen that in increasing the annealing temperature increases the grain size. And one more features we can observe here for two-phase alloys. In contrast to single-phase materials have grain and interface boundaries. It means different type of boundaries. that can influence on the mechanism of electroplastic effect. So we again can observe that if we use single current or multiple current and at temperature not more than 240 degrees, we can reduce the flow stress by 25 or 30%. It's very good results if we think about the application of this process for two-phase materials. So I should note that no microstructure difference were observed between the reference tensile test and the materials stressed under electrical current. So this is microstructure in longitudinal or in cross sections. So we cannot see secondary phases. And conclusions. Tensile electroplastic effect has been studied in pure metals and alloys, differing in structure and phase states. It is demonstrated electroplastic effect manifestation can be different from known examples in the literature. First, anomalous effect of hardening instead of softening. Of course, caused by reversible martensitic transformation in shape memory alloys. Strengthening can also be observed not only for such materials, but for pure metals under tension with single current pulses. An important consequence of electroplastic rolling is grain refinement to nano-sized area. And many experiments indicate that electroplastic effect contribution to stress reduction is noticeably greater than the contribution from jaw heating at the same test temperature. Thank you.
Thank you, Professor Stolyarov. We have about 1 or 2 minutes for questions. Colleagues, do you have any questions?
No.
One moment, I lost my presentation. Yeah, I see.
Oh, you're welcome.
Vladimir Vladimirovich, can you say what's the reason for in difference in tiny alloy in stoichiometrical and not stoichiometrical composition and in the effect?
So you mean what's the reason for sequences of the effect?
Differences in tiny alloy with different composition, stoichiometrical and non-stoichiometric.
Okay, in both materials we have two kind of transformation. First, austenite to martensite for behind stoichiometric materials, and we have only martensitic reorientation. So it's important to understand what's kind of electroplastic effect in this area. So we see, one moment, I will know. For titanium nickel behind stoichiometric,
this one.
The first we can see shape memory effect. This is but for electroplastic effect we can see on the following stage, and the working stage. For another alloy, for stoichiometric alloys, this is opposite. In the starting we have electroplastic effect, so the down stress, and after that up. So the current transformation, that is the reason.
Thank you very much.
Okay, thank you. So next report from Evgeny Naydenkin.
Thank you very much. And first of all, I would like to express my gratitude to organizing committee for inviting me to make presentation on a conference dedicated to Professor Zhilyaev. And it was really shocked for me when I knew about his death in the end of last year. The title of my today presentation is changed a bit, and then now it's sounds like effect of severe plastic deformation on structure, mechanical and fatigue properties of near beta titanium alloy. And here my co-authors, my colleagues, and the motivation of the study is obtaining of alloy with higher strength and fatigue properties for possible practical application, for example, in aerospace industry. And here the chemical composition of the investigated alloy, some investigation methods, and two different techniques for obtaining of ultrafine grain structure were obtained. It's a famous method of multiple pressing with temperature step down, and it's a very quite famous technique. And the second one, a more new technique, it's radial shear rolling, which in the case was used with combination with subsequent agent. And we use the mill for radial shear rolling, designed in Mises Institute. And here the scheme of the process of deformation. And the result we obtained were rods with different diameter, beginning from 22 millimeters and low, and with a length about 1 meter. After the rolling, we use the agent. And in the case of multiple pressing, the imposed strain about 8 true logarithmic strain, and in the case of radial shear rolling, the strains are few less, about 1.7. But you can see that the mechanical properties is quite comparable. I must say that we have more than 15 year experience in obtaining ultrafine grain structure of titanium alloy with different different classes, and you can see from here that with increase of alloy elements, especially beta stabilizing elements, vanadium and molybdenum, the contribution of grain refinement and strengthening decreases because of the increase of solid solution strengthening effect. After the multiple pressing, we obtained the dual phase microstructure, quite homogeneous, with grain size about 200 nanometers and quite 50 to 50 phase composition, alpha and beta phases, according to the X-ray study. And the composition is very homogeneous in the whole sample. And in comparison with multiple pressing, the radial shear rolling result in more coarser structure. It's a cross section, and grain size of beta phase about before aging about 5 microns, and you can see the alpha primary phase on the grain boundaries. Here you can see it by transmission electron microscopy, and then some grain size here is about 400 or 700 nanometers. And after the aging, we obtained the dissolution of beta transform matrix with precipitation of acicular alpha or alpha double prime particles inside better deformed grains or subgrains, and as a result we obtain about 62% of alpha and 38% of beta phases in volume fraction. As a result of such difference in microstructure, we obtain in the same alloy different mechanical properties and mechanical behavior. You can see that the alloy in initial state, and after the multiple pressing, we conceive the typical for SPD produced material with a with a short stage of deformation strengthening and with a very long stretch of deformation hardening, deformation softening. As to the alloy produced by radial shower rolling with subsequent agent, we can see that the deformation curve looks like an initial state, but with a short, with a low ductility. But if you consider on elongation, uniform elongation, that in the case of multiple pressing it's less than 1%, but in the case of radial shower rolling and agent, it's more than twice higher, but more than 2%. Its value very important for practical application of the alloy, and as a result of the structure, the different fracture mode realized in the two materials, practically ductile fracture in the case of multiple alloy produced by multiple pressing, but in the case of alloy produced by radial shower rolling agent, it's more brittle fracture realized. We also investigate the influence of agent in air and oxidation of the alloy, because it's very important for also for practical application for agent, because the agent usually treatment usually provided in air, and we obtain that the alpha case formation with a thickness about 2 micrometer meters on after the agent at 550 degrees Celsius, and with formation of oxide or alpha case layer. As a result of the oxidation, we in the case of the alloy produced by radial shower rolling agent, we obtain the simultaneous decrease in strength and ductility that is quite unexpected for titanium alloy, because in the case of alpha or alpha plus beta titanium alloy, the oxidation results in decrease in ductility, but in increase in strength because of oxygen solid solution strengthening. But we investigate the reason for such unexpected behavior of the alloy, and we reveal that after that the reason for decrease in ductility is after the alloy with oxide layer is formation of microcracks on the surface of the alloy, whose density and depth increase with increasing of strain. And this is differences in fracture surfaces of this alloy. Just here you consider the alloy without oxide layer, it's practically ductile fracture, and now it's a practically brittle fracture in the alloy with oxide layer. We investigate the by light profiler investigates the depth of the microcracks, and we reveal that in with the strain, the depth increase the thickness of the oxide layer, And this is a result of, in fact, the result in brittle fracture of the alloy with oxide layer. But what about the reason of decrease in mechanical strength of the alloy? Then we investigate the depth of oxygen in the alloy after aging, and then we observe that the oxygen-rich layer in the case after annealing is about 12 micrometer thick. And this result in differences in dissolution of beta phase dissolution and with precipitation of more coarse alpha particles or alpha precipitation, and this is resulting in decrease in micro hardness in near surface layers, and of course it's result in decrease in strength of sample in whole. And I already said that we also investigate the fatigue properties of the alloy. It's very important for practical application. And here the installation for such investigation with ultrasonic frequency. And here the specimen for investigation. And the compression of each sample were cooled by compressed air, and we obtained that the formation of ultrafine gray structure by radial Sharon with agent result in increase in strength, in fatigue strength and fatigue endurance of the alloy. You can see the even with the number of cycles to failure more than 10 and 7, the stress amplitudes reach more than 800 MPa. That is very high values for titanium alloys, and when the number of cycles to failure reach or more than 10 and 9, then stress amplitude achieve the 635 MPa, also very high strength value. And we also investigate the fracture mode, and in both cases, in all cases of it's internal fracture mode with formation of famous area as a fisheye area, fisheye rupture area, and we investigate the original and the microcracks initiation original, and here the quite different mode of with electrical fisheye or smooth area fracture zone, but with the same view of microcrack initiation area. We also analyze smooth fracture area with number of cycle to failure and initial stress intensity factor, which responsible for microcrack initiation and fatigue crack growth in very high cycle fatigue tests. And we in all cases this value exceeds higher than 25, and it's very high value for titanium alloys, and it's very good combination, and even for very high number of cycle to failure. And we also investigate some places and some crack initiation area, and we reveal that the microcrack initiated in the interfaces between alpha primary particles and beta transform matrix, and this is this is area, and this result supported by transmission electron microscopy on the area near from fracture. This is some conclusion, and the main results, I didn't read it, but the main results, it's the alloy demonstrate very high strength, mechanical strength and fatigue resistance, and very high ability for some practical application in the, for example, for aerospace material constructions. So, and some picture of Alexey Zherebtsov, who was also a friend of mine and from Nano SPD conference from Fukuoka, 2005, and thank you very much.
Thank you for your report. We have 2 minutes for questions. Colleagues, you're welcome.
May I?
Oh, yes, of course.
I did notice if you evaluate texture effect on strength parameters.
Sorry? Texture about
yeah,
radial shear rolling?
Yes, mainly.
Yeah, but we studied, but I didn't include it in the investigation. We, of course, with some kind of texture observed in the material, and it's changed from the central of rod to the end of the rod, and so it's a quite famous, but because the deformation in the center and then in the edge is very different. But using the special regions of deformation, we obtain the material with quite homogeneous structure in the center and the edge of the rod, and with quite homogeneous microstructure distribution is very very important. And so that's allow us to obtain the material with high fatigue properties, because its fatigue is very sensitive for non-homogeneous microstructure as well.
Thank you.
So thank you for report. And next report is going from Spain, from Maria Teresa Perez Prado.
Hello.
If I correct. I'm glad to see you. You're welcome.
Okay, thank you very much. First of all, Madrid, and I would like to tribute to Alexander Zhilyaev, who was only a mentor, but also a very dear friend. I met Alex at the Naval Postgraduate School in California. And well, this seems. I have been a witness of his very provide the best for his family while producing excellent. His ideas motivated phase transformations. We publish about 10 or 12 to the beginning of my or research group. So I am very thankful with him, and I will miss him very deeply. Today, I'm not going to talk about sharing about more of our recent work. So what I'm going to try to work in trying to solve 2 questions. One is the precipitates on the sleep activity in magnesium. So why worry about this? There is quite a controversy. On the one hand, I'm going to start from solute atoms. No, some it's aluminum or zinc to magnesium. We change the sleep system. the reason why when we add these elements, we suddenly see and a simultaneous increase in strength. In order to try to contribute to this, what polycrystals, 6 polycrystals of which are the ones that I'm showing you here, and then another aluminum alloys. So what are these 6 maps? The magnesium zinc alloys, and on the left hand magnesium with 1% zinc, and on the right 2% zinc. And then the rows we have called small, medium, and large grain size. Approximately on average 5. This is the small one. Sizes and about 34, 35, 36 microns. What we call the large grain size polycrystal. So we decided, and also again, these are the in a series of magnesium aluminum alloys, and these are ordered the same. So on the left hand side, we have magnesium with 1 weight % aluminum, with 2 weight % aluminum, and again in medium and large grain sizes. In both cases, these were produced by rolling an anneal basal texture, which means that the of these HCP crystals, for those that are not so familiar with magnesium, and this is aligned with the normal to the rolling direction. So red, this is they have. What we did was to test these materials, and here curves corresponding to let me see if I there you can see it better. Yes, so these are curves corresponding to all these 12 polycrystals. So and at room temperature and a standard, you can see the curves corresponding to the zinc polycrystals, because we are going to analyze the data later. On the right hand side, we have the curves corresponding to the magnesium aluminum. Here I am plotting addition of aluminum and zinc for the different grains. Here A is the yield strength, and the data corresponding to pure magnesium polycrystals of similar grain sizes that are small, medium, and large. Presentation for the UTS, and down here we have. So as and then in red we have the data. Blue we have the data corresponding to the magnesium aluminum. What do we see? Well, as expected, we see that we have an increase in the strength, here, and also in the ductility, right? So this is the results consistent with what is known. But are especially important in the polycrystals. In the yield strength, the increase is higher. The ductility. So what we went on to try to perhaps give us a clue as to what is really the effect. And that's what we tried to analyze. To study a sleep trace analysis study to understand the dominant deformation mechanisms, and we analyzed in the surface of each of these polycrystals the frequency of sleep traces become active in magnesium alloys, basal. And on the left-hand side, for the zinc polycrystals, on the So we observed, as also it is quite of the grain size, irrespective of the composition, based. So what we went to see is, okay, the addition of these solutes must be, they do. And the microstructure of these polycrystals in a little bit more detail. I'm showing you 4 histograms that correspond. That these were the ones where we observed the higher. So I have here in black, this is 1% zinc, 2% zinc, and 2% aluminum. And in red, we have the, sorry, so in black, we have pure magnesium corresponding to these alloys. All of them, polycrystal, is that when we add the solutes, or aluminum, what we have is a decrease smaller than 30 degrees. And this happens in. Now, does the same happen when we? The answer is no. No. Here again, we are comparing the misorientation distribution histogram black, and for the different alloys. When we have large grain size polycrystal, the addition really doesn't have a very strong influence. Here we have a little bit of difference. In some cases, there is a small misorientation angles smaller than 30, much less pronounced than in the case of the fine grain. That the fact that the solute could be at the origin of this of in ductility and strength that we observe. One step further, and what we did was know that basal slip is by far the main dolphin, and we know that when we add the solutes in the polycrystal action in these boundaries that have low misorientations. It from previous work, but it seems it's also. These are the ones that favor slip. And so what we did was to try to analyze what is the connect for basal slip, trying to see whether more favored than in others. So what we did is we classify junctions, as you can see here. No, we with a Schmidt factor for basal slip the connectivity of these grains by analyzing and classifying. So the boundaries that are colored in red, they have this, and they favor basal slip transfer, and the boundaries angles higher than 30%, and they don't favor these triple junctions in these 4 types that you can see here. Junctions that do favor basal slip transfer, and J1 favor basal slip transfer. So then we measured the data, no, this frequency of the J2 and J3 triple junction that favor a slip transfer between the grains, black dots here, and in the different alloys for the 3 grain size ranges. Somehow, excuse me. 3 grain size ranges that we are investigating. And grain size polycrystals, there was almost no well oriented for basal sleep, but for the addition of this zinc and aluminum solute, small decrease, a very large. So what is the conclusion between aluminum to well oriented for basal sleep become less connected, and therefore sleep localization. Because sleep localization is prevented, the material strains and also be stronger. The take-home message from this is that when we add atomic solutes or just atoms, this has a multi-scale conditioning and influencing, for example, the effect of atoms, but we also are changing the microstructure. I have about 5 more minutes. Okay, so this is the first part of the talk. I'll go. The second part deals more with magnesium alloys. It's very hard to strengthen them by precipitation. We did is to analyze this is not possible. Basically, as I showed before, they deform by basal sleep. For us, in principle, and what can mostly ability of strengthened magnesium alloys by precipitation is with the precipitates. So in order to use this alloy that you can see here is a rare earth alloy, neodymium. This is the as extruded state. It has the maps on the right. It show you the microstructure 175C. After precipitation takes place, and precipitates are plates that are parallel to these prismatic planes. You see this cross section here, but when you zone axis, you see the plates. No, you see this. What is important is what I was mentioning before, that at room temperature of the in blue. The material is in 2 conditions, and you can see very small. So let's see how these locations, and especially precipitates. Here is you can see these TM images where this plate precipitates. Here, this is the trace of a base. These basal dislocations cut through the precipitate of interaction. So because the matrix and these precipitates that form in most these locations to cut through them, and that's why they are not. This is a nice image. I mean, we observed in several alloys, but then we went on to what happens with prismatic dislocations. And image here on the left, where you can see this is a this plate precipitates, and these are all of them are able to loop the precipitate. Also, some of them, you can see here some certain prismatic planes, pyramid locations can loop the precipitates. An example of here in the precipitates, and the reason why these locations move in very different planes and the coherency effect in the matrix and in the precipitate is different. Interaction mechanism, depending on this I think I'm running out of time, so I'll just talk. These were just some other examples. Show this last image where you can see that indeed no geometry, the size and the dispersion alloys. This is, for example, a gadolinium. See at a very atomic scale how this can also shear this type of precipitates. Just conclude that because of this intense shearing and that, well, non-basal dislocations and loop or shear, but these are not the main strain carriers. But it's not, doesn't have such a big impact in the mechanics. Very much for the invitation and for slide to thank all my team members and the thank you very much.
Thank you, Professor Prado. Unfortunately, we ran out from the time. Colleagues, if you have any questions, but very short questions.
Hello. Can I ask a question? If you
yes, Daria, you're welcome.
Yeah, thank you for your report. It was very interesting and very useful. At the beginning of the report, you show that you provide tensile tension only in rolling direction. Is it right? I mean, whether you try to perform such experiment using the perpendicular direction.
This is the slide you're referring to exactly. Well, a bit of a lack of time, no? Because we had in this get some let's say statistical information, so we testing the testing condition and rather use a wide compositions and so on. The tensile conditions carry out the same test, different deformation mechanisms. No, we would is a role. So we wanted, we had to fix conditions in order to have this then expand in the types of materials and in grain size. Interesting, no? To now do it in another direction.
Okay,
thank you.
Okay, thank you. The last report in this section is going from Korea, University of Science and Technology. Professor Kim, you're welcome.
Yeah. Can you hear me?
Yes.
I'm Kim from Korea State. It's my pleasure to be here and give my talk. Although it's not as good as the offline meeting. I'm here for the memory of our nice friend, Alex. The title of my talk is here, multi-layered gradient structure by singular angular rolling, a kind of severe transformation. Sorry. So this is with Alex 3 years ago in St. Petersburg. We had a very good memory, and I always had a very good discussion with him. And he's a real scientist, I remember. Okay, today's what I want to talk is the first, continuous transformation, and second, heterostructuring based on the continuous processing, I call it SRAS, the single roll angle rolling, and the surface nanostructuring is also applied. So the microstructure and mechanical properties of the layered structures was introduced. In metallic materials that are most widely used as a structural materials, the high strength is the most important factor to expand mechanical stability. Therefore, severe plastic formation for grain refinement has received great attention over the past decades as an innovative technology for high strength. SPD is a process that applies strong high pressure, hydrostatic pressure, and shear deformation to metallic materials, thereby minimizing the grain size of the material to ultrafine or nanocrystalline materials. Therefore, SPD process with the high strength that is several times higher than that of conventional materials due to grain refinement and high work hardening capacity. In addition, research on SPD process has been actively conducted as it stands out various functional properties such as biocompatibility and corrosion sometimes. Nevertheless, recent research on SPD has been pointed out that industrialization is not easy in two aspects. First, the size effect. Size of the manufactured specimen is quite small, limited, compared to the equipment output required for grain refinement. Second, because most of the SPD processes have discontinuous design, and there is a lot of specimen loss during the repeating processes. And the efficiency for mass production is considerably low. Above all, the strength increase rapidly by grain refinement, but on the other hand, it does not have enough toughness to be used in various industrial parts due to the trade-off dilemma of strength and ductility, where ductility decreases sharply. Therefore, for industrialization of the current SPD processes, such low productivity and poor toughness are challenging that must be solved. Therefore, in the SPD society, in order to overcome the low productivity, various continuous SPD has been developed based on existing ECAP process. ECAP is the process that applies high shear deformation to workpiece by pressing metal bar into a channel bent at a specific angle, as shown here. The ECAP process has a low load equipment than the other SPD processes, so it is possible to perform a sufficient continuous processing by combining its rotating roll. Accordingly, various continuous SPD processes such as ECAP conform, next figure, conform has been introduced. Accordingly, various continuous process was developed, but nevertheless, even in this continuous SPD process, poor toughness or dilemma of the trade-off strength and ductility is still a very important issue. The EK conform processes here enhance the drag force by changing of the cross-sectional shape from circular to square. During the transition of the cross-sectional shape from circular to square, square to circular, the channel dimension is the same. The distribution of the equivalent strain is similar to the ECAP because most of the deformation is applied here. However, the ECAP process, ECAP conform process is not available to thin sheet shape, and there is no circumferential shear strain dragging in the region. The continuous process I have developed is a process called single roll angular rolling because it's a same as a roll, but it is only one roll. As you can see here, the SRAR is a continuous SPD process for metal sheet or plate, and it is possible to perform the process simply by inserting the rotating roll here inside the specially designed outer roll. The metal plate is subject to high rigid plastic formation as it moves along this rotating die. And the workpiece is divided into two regions. First, the circumferential area, this area, and facing the rotating roll. It is designed to introduce a continuous and strong driving force on the metal plate by gradually decreasing the gap thickness from 1 millimeter to 0.96 millimeter. Later in a channel region like E cap, the gap is bent sharply, in our case 135 degrees, at the end of the circumferential area, and strong shear deformation is applied to metal plate. This process is designed to thickness of the metal plate before and after the processing is the same, so we can repeat it as many times as we want. So now I explain this SRAR process as a heterostructuring material. Recently, in order to overcome the strength ductility trade-off, heterostructuring design is emerging as a new microstructural design concept or strategy. Heterostructural materials refer to a material that has a relatively soft area and hard area by artificially heteronizing the microstructure, so deviating from the classical viewpoint of a homogeneous microstructure. The well-designed heterostructuring material shows excellent mechanical properties with high strength and high ductility, like here, at the same time compared to conventional homogeneous material here. Material can be customized with the various structures and properties according to the various microstructural variables, such as spatial distribution, domain area, area fraction between hard and soft material, soft region, and grain size distribution, etc. However, in structuring heterostructuring process developed so far, controllable microstructural variables are quite limited. Developing new heterostructuring processes and expanding microstructural control parameter is a continuing challenge in this field. The circumferential area, and there's also channel area, can cause complex deformation history for the sheet. First, in the complex circumferential region or hoop region, the higher negative shear deformation is accumulated on this sheet here. After that, the metal plate is subject to relatively uniform and strong deformation like E cap. At the same time, additional shear deformation occurs due to the friction after this force. So therefore, the SRAB process can cause different level of shear deformation in the central and surface of the metal plate by combining these 2 or 3 deformation modes. The SRAB process has the characteristic of being able to control the level of shear deformation of the surface and the center of the plate, as shown in this figure. The center, this length of the arrow represents the shear deformation. The results of the experimenter on pure copper plate are this. The TD, transfer direction side picture, after repeating the SRAB process 6 times here, a copper plate is the initial coarse grain material and it was uniform. Now we can see that larger amount of shear deformation accumulates in the center region. Center shows the finer grains compared to the surface area, resulting in a lot of distortion and inclination of the microstructure. Since this different shear deformation in the surface and the center region induce different recrystallization and grain growth behavior during subsequent heat treatment, the subsequent heat treatment, this is after post-elongation, subsequent heat treatment. The heterostructure is very unique with a relative fine layer in the center and coarse layer in the surface. So we named it as an inverse gradient structure because general gradient structures are coarse in the center and fine in the surface, but it's reverse. The USA analysis under inverse or reverse gradient structure confirmed that almost complete recrystallization occurred through the thickness after this post heat treatment. Next, let's see the processing pathway called route A, route C. Because Srab process can repeat it because the initial thickness or final thickness is the same, we can repeat like ECAP or cumulative roll bonding. The microstructure and physical properties may vary depending on how the plate is rotated between repeating process. As you can see here, the Srab process can be performed in two ways, route A, route C, like ECAP. Route A is the process path in which the subsequent process is performed without rotating the specimen between the repeating process. In order to analyze the shear deformation of the material according to each path, I performed finite element modeling. The FEM simulation results, the route A confirm that shear strain is double, like route A. This is the one path, and this is the route C. The shear level of the center and the shear level of the sheet are further divided. On the other hand, the route C, the blue one, shows significantly low shear strain because the first shear and second shear direction are reversed. This is because in case of route C, as shown in the figure, the shear deformation due to reverse shear occurs at every even number of processes within the same shear plane. The distribution of shear strain along the thickness direction of the sheet by each process is as follows. In route A, the amount of process increases, the shear strain is more effectively divided in the center and the surface. So it was confirmed that microstructure was quite heterogeneous, layered and gradient in the center and surface of the plate. The major dislocation density and grain size for the center and the dislocation density and grain size, the center and surface of the plate confirmed that grain refinement and high dislocation density appeared in the center of the plate and high dislocation density as well. On the other hand, route C, the difference between surface and the center was insignificant because the overall shear strain is cancelled. And the microstructural heterogeneity in the center and surface was insignificant. It's not important. Therefore, through this experiment, it was confirmed that route A is more efficient process route in terms of the microstructural heterogeneity compared to route C. Next is the subsequent heat treatment effect. The 6 times route A Srab process sample was heat treated. These conditions. As a result, 3 types of inverse gradient structure were produced. As the heat treatment time increases, the fraction of the microcrystalline layers in the center of the sheet decreases, while the grain size was constant for all the material. As the last processing, we refine surface. As you can see in Srab, the surface is coarse. So at this time, I'd like to make a fine grain surface that make a layered by layered material. I used the UNSM, ultrafine nanocrystalline surface modification. It's like a SMAT developed in China. So I call it UNSM, ultrasonic nanocrystalline surface modification, UNSM. Oops. UNSM is for multiple heterostructuring. The Srab process mainly defines the center of the plate, and UNSM mainly defines the surface, then resulting in a new gradient structure that maximizes the heterostructuring. The heterostructure produced through the multiple heterostructuring, coarse, fine, is as follows. The EBSD surface of the UNSM sample confirmed that grain refinement was induced at the level of 5 micrometers. It's not quite small, but it's fine. The average grain size distribution in the thickness along the thickness direction from the bottom to surface shows that additional grain size gradient was confirmed on both surface of the material with the inverse gradient structures. The surface is fine due to the UNSM, and center is fine due to the SRAR process. Therefore, this material shows, a multi-layered gradient structure along the thickness direction of the plate, and the microstructural heterogeneity was intensified through this multiple heterostructuring of combined SRAR and UNSM. The next is mechanical properties. The overall properties of the material according to process history or of multiple heterostructuring is as follows. Its initial, and the red one is SRAR, the blue one is SRAR plus surface nanostructuring. Both heterostructured SRAR process and the SRAR plus UNSM material showed excellent mechanical properties, good combination of strength and ductility. First of all, in the SRAR plus UNSM, this is engineering, this is true behavior. Although the elastic strength increases by 2 times from almost 1 to almost 200 compared to the SRAR materials, there was no significant loss of toughness. Toughness means this area, strength multiplied by strain. Therefore, in terms of the structural materials where shape maintenance is important, the SRAR plus UNSM materials with high strength, high yield strengths are more preferred. Finally, the mechanical properties of the heterostructural material processed through this study is as follows. This is the SPD, is very high strength, but low elongation, and reverse material with SRAR material shows low yield strength, but good toughness, energy, but multiple gradient materials. SRAR fine, coarse, 4-layered material shows very good combination. The general SPD process increases the strength rapidly, as shown in this figure, but decreases toughness. However, the heterostructuring used in the SRAR process shows simultaneous increased strength and toughness or fracture energy. The properties of the heterostructuring material produced excellent mechanical properties. That is the trade-off of the strength and ductility. This trade-off was overcome by using this layered material. Through the subsequent UNSM process, multi-layers gradient structure material with more heterogeneous generality showed a high synergy of strength and toughness through the proper combination of HDI strengthening with mechanism, heterodeformation-induced strengthening, and HDI hardening. Okay, thank you very much, sir, for your kind attention.
So, thank you for your presentation. Colleagues, one short question. Maybe somebody from conference hall in Mr. Yu?
Thank you for very interesting presentation. And could you compare the results of the gradient structure between your process and maybe a symmetric rolling process? What is more perspective in your opinion?
I didn't compare by myself, but I think, yeah, in deformation strengthening mechanism, as I said, HDI strengthening is high in the layer structure or gradient structure. So instead of the other simple fine-grained materials or just normal gradient materials, this is the more layers that the geometrical necessary dislocation G and D accumulate in the interface more than the inside and outside. That's why this will show higher strengthening, I think, and plus combination of good ductility. But I didn't compare by myself, so we can compare it.
Thank you.
Thank you.
So colleagues, thank you for your attention.
Thank you.
It was difficult for big number of reports. Now we have short coffee break, just for 20 minutes, and we will start from the second part of our schedule. Stay online. Thank you. So, colleagues, we should continue. The first report in this section is report of Vasily Astanin from Ufa State Aviation Technical University. Vasily, are you here?
Yes, I'm here.
So, you're welcome. You can start your demonstration.
Okay, let's start it. Good afternoon. I present report features of deformation of amorphous zirconium-based alloys subjected to high-pressure torsion. Amorphous alloys are a relatively new class of materials that are of great scientific and practical interest due to their unique structure and properties, high strength and low modulus. Their peculiarity lies in the fact that since there is no crystalline structure, there is no dislocation structure as well, and deformation is carried out by formation of shear bands. And at the elevated temperature, the deformation is carried out homogeneously. Upon compression or bending, bulk metallic glasses exhibit some ductility, but the main problem for amorphous alloys is brittle fracture during tension. Many efforts has been put to improve plasticity. In some articles, it was shown that one of the methods for increasing plasticity is preliminary severe plastic deformation, in particular high-pressure torsion. The goal of this work is to study the features of deformation mechanisms and mechanical properties of bulk metallic glasses subjected to severe plastic deformation. The research material is the zirconium alloy, which is quite common and is considered one of the best alloys of this type in terms of strength and ductility during compression. The composition of the alloy is shown on the slide. Samples were subjected to high-pressure torsion in various modes, from 1/18 to 30 revolutions. To study shear bands, a new technique was proposed and developed, the technique of torsion of two halves with polished end surfaces. After high-pressure torsion, the shear bands come out on the end surfaces in the form of steps, and they can be measured. The scheme for obtaining such a picture is shown on the slide, as well as the end face of the half after high pressure torsion. Nevertheless, traces of shear bands are well detected by scanning electron microscopy method on the end surfaces of the halves. It is shown that as the number of revolutions increases during high pressure torsion, a larger number of shear bands are formed in the samples, which forms a deformation pattern. It should be noted that the traces of the shear bands in the form of steps only is the first approximation reflects the actual density of the shear bands in the sample, since the actual spatial position is unknown. However, the formation of large number of bands should have an impact on mechanical properties. It can be seen that with increase the number of revolutions, the distance between shear bands decreases, respectively. The density of the bands increases, and the 5 revolutions, the minimum distance is about 0.5 micrometers. Thus, the entire volume of the material accumulates a high density of shear bands. Since it's known that the structure is transformed at a distance of 10 nanomicrometers from the band, it can be argued that the entire volume of material is transformed. At the edge of the sample, where the strain is highest, a fractal-like pattern is formed. The fragments of the material, divided by primary bands, are themselves divided further by bands of lower intensity into smaller volumes. The distance between primary shear bands is 20 to 100 micrometers. Between the smallest one, it reaches 70 nanometers, on average about 150 nanometers. Crystalline inclusions were noted in some areas of the sample. It can be seen that amorphous matrix surrounding the crystalline inclusion is deformed with the formation of shear bands. At the same time, there are no shear bands in crystalline inclusion, but the cracks are formed, which indicates a low plasticity of the intermetallic phase compared to the amorphous one. At the same time, a very curious picture appears on the intersection of two band systems. On the one hand, the shear band can merge into bundle and overcome a shear band barrier. On the other hand, when approaching another barrier, the shear bands are fragmented, forming a delta of small secondary bands. The friction that occurs at shear bands at shear surface results in an increase in temperature, which further facilitates shear propagation. For same reasons, the combination of thin shear bands into larger shear bands can occur. The shift along the shear bands leads to local stress relief and a change in the stress state of the adjacent volumes. In addition, the propagating heat from the shear bands facilitates the shift towards the temperature gradient towards the shear band. A combination of factors causes the appearance of transverse shears in the form of streams flowing down to the main shear bands. For the same reasons, intersecting bands can merge. If the shear band meets an impassable obstacle in the form of another shear band, then when approaching it, it is divided into small lanes, forming a kind of delta on right lower image. In the other cases, sufficiently intense shear bands can create high stress concentration and able to overcome obstacles. Other bands forming steps on them. However, when using this method, it's turned out the expected strain is not achieved. This slide shows bulk metallic glasses halves deformed to various strain using high pressure torsion. A sample of 2 halves of copper after high pressure torsion by a quarter turn receives a real deformation expected by well-known ratio first ratio, which is evident from the displacement by the corresponding angle of the upper part of the sample relative to the lower one. According to our calculation, the real strain of bulk metallic glasses is 100 times less than predicted by well-known formula. To overcome this limitation in strain, a new deformation scheme was proposed, a cumulative high-pressure torsion. Detailed report on it and why exactly structure transformation is still taking place even in the conventional high-pressure torsion, please see Gunderov's report tomorrow. It will be explained. This amorphous alloy remains amorphous after high-pressure torsion. No significant nanocrystallization was observed, neither according to the results of X-ray analysis nor according to differential scanning colorimetry. However, the structural transformation still occurs. The position of characteristic points on DSC and the amorphous halo change slightly. The X-ray halo shifts towards smaller angles, showing an increase in the free volume and increase in the radius of the first coordination sphere. Distance between the distance between atoms increases. The relaxation energies also change, so all the data indicate an increase in free volume and increase in non-equilibrium as a result of high-pressure torsion, and especially strongly in the case of accumulative high-pressure torsion. The slide shows transmitting electron microscopy results for PMG samples of the initial stage and after high-pressure torsion. The pictures show that our results do not allow to visualize shear bands. There is no contrast from the bands. Transmitting electron microscopy after cumulative high-pressure torsion doesn't reveal any specific features. The bands are still not observed. No significant nanocrystallization was observed according to the results of electron diffraction. Only in some areas there is fragmentation of the diffraction halo. Meanwhile, colleagues from Germany managed to visualize the band in the transmitting electron microscopy using special technique using oxygen decoration, but this way is not suitable for extended analysis. The effect of modified structure on properties is assessed using tensile tests. Tensile tests on small BMG samples of the S-cast material and after high pressure torsion on various regimes did not show any signs of plasticity. All samples were fragile. It is possible that during tensile tests, the working part of the samples falls right into the center of HPT circle, so there is no significant change in properties in this point. Anyway, plasticity was evaluated using microindentation and atomic force microscopy method. Plasticity is estimated by the size of elevations near the indents, but it's not correct to directly compare it. It's necessary to correct the value of hardness according to the method proposed by Professor Glaser. It can be seen that plasticity is high after 2 revolutions, but for 5 revolutions it decreases. And microhardness is lower after high pressure torsion, which is quite common result for amorphous alloys. So shear bands act as an obstacles. We were able to reach a high density of shear bands, and bulk metallic glasses retain its amorphous structure during high pressure torsion. That's all for now. Thanks.
Thank you for your report. I want to ask our audience, do you have any questions? I have a few questions because this is not question, but just for discussion. Do you plan to make some kind of computer simulation of such treatment of such materials?
Yes, we're currently in process of it. Tomorrow will be a report by Mr. Gunderov exactly on computer simulation of high pressure torsion and why it still has some effect on structure and properties, even if we do not observe any strain during it. We observe strain 100 times less than expected, but properties still change.
Okay. Why I asked? Because our colleagues from AGH University in Krakow in Poland, they developed a special method with software, of course, it's so on and so forth. Special method for simulation of shear bands oriented deformation. This method is based on cellular automata method because sometimes traditional commercial software is not suitable for some interesting materials. This is only for the discussion. And
yeah, that would be quite interesting because it's really, yes, that's the problem that commercial software does not support well shear banding.
Yes, and they connected.
We're currently working on it.
They connected two methods, so finite element simulation and cellular automata, клеточные автоматы, so-called cave models, especially for connecting commercial software like Abacus and SYS with some artificial software, artificial scripts in Python for simulation of such materials. And also one question about practical application of such materials and such methods. So maybe you have some results about the biggest size of product which can produce by this method from these materials.
Generally, bulk metallic glasses do not exceed a few millimeters in lowest dimension. Some alloys allow to achieve something about 10 or up to 40 millimeters in lowest dimension, but it's not quite common. Actually, commercial application of amorphous alloy bulk metallic glasses, I think it's still in the future. No one can really produce a significant amount of this. And the main problem that limits its commercial application, properties are quite unique: high strength, low modulus, good corrosion resistance. They are perfect. But their low plasticity, extremely low plasticity during tension, limits the commercial application. So goal of this work, when we first started it, was to try to improve some plasticity, but it's not quite straightforward.
Is it expensive material?
It's not available as a commercial material, so it's quite, it's not abundant, I'd say. No, not many people producing it. It's mainly produced by the universities in the labs, so it has no commercial price.
And you answered for my next question about initial billet. Where can I obtain such material in internet, in some commercial laboratories, or not?
It's almost impossible. There is a company in the United States which produces liquid metal, but they I have no contacts with them, so mostly it's produced in university labs. My material was produced in Nanjing University, Nanjing University of Science and Technology, thanks to Professor Wang. Some part of the work was done on American material.
And the potential application, as I understood from name of your university, for aviation and so on and so forth. Yes?
Actually, I believe it's more medical. Can have medical application in much better way.
Okay. It's really interesting and perspective, I think.
I hope so.
Colleagues, do you have any questions? No.
Okay, no questions.
Okay. Good luck.
Thank you for your attention. Good luck.
Okay, thank you. So next report goes from Russia, from Sergey Zherebtsov. Sergey, are you here?
I'm sorry, Sergey is not here, but I'll start his presentation on his behalf.
Okay, you're welcome.
Dear colleagues, my name is Sergey Zherebtsov. I'm from Belgrade State University. My talk is about structure and properties of titanium-rich high-entropy alloys. A well-known way to obtain a good combination of strength and conductivity in some FCC metals is activation some specific deformation mechanism like transformation-induced plasticity, twinning-induced plasticity, or microband-induced plasticity. The activation of each of those mechanisms depends on the value of stacking fault energy. In fact, similar effect can also be observed in some BCC titanium-based alloys, but in this case, the realization of those mechanisms does not, in fact, depends on the values of stack and fault energy. So the question is if it's possible to realize similar specific mechanism in BCC titanium-based high entropy alloys to obtain very high strength and activity. Today I'm going to consider two cases. The first one is activation of trip effect into this alloy comprising titanium, zirconium, cadmium, tantalum, and tin in comparison with already known titanium, zirconium, gadmium, niobium, tantalum alloy. The first alloy, this one, was developed by Lilestein Carters using a so-called Bohr-MD approach. This approach is widely used for development of titanium alloys to find a composition which can show trip-trip effects. Here, Bohr means bond order, and then means d orbital energy level. Lilestein with the co-author first proposed to use this approach to develop titanium-rich high entropy alloys, which also could demonstrate trip effect. And since these alloys were found to be deformed using phase transformation, they put this line, the line of instability, like here. And we also tried to propose two alloys with different, little bit different composition. Here, alloy number 2, exactly at this line of instability, and the alloy number 3 is little bit below this line. All three alloys were produced by vacuum arc melting. Mechanical properties of the alloys in as-cast condition was evaluated using tensile test, and structure characterization was made using TM, SAM, including PBSD analysis, and also phase composition was controlled by X-ray diffraction. Here you can see microstructure of all three alloys in the as-cast condition. The microstructure of all three alloys is two-phase, comprising beta matrix and precipitation of the alpha prime phase. In some cases, we can see small twins in the martensitic alpha phase. And these alloys shows very interesting mechanical properties, especially the alloy with two parts of tin. You can see that this alloy shows very high strength and find quite pronounced elongation in comparison with the alloy produced by Dr. Lindstein. And this mechanical properties, very high strength and ductility, was most probably caused by very good ability of this alloy to strain hardening. And this double curve of hardening suggests the development of some specific deformation mechanism like twinning or phase transformation. In this table, you can see the level of properties which can be obtained in this alloy. Tensile maximum design strength almost 1 GPa and engineering elongation 26%, which is quite nice. And indeed, if we see at the microstructure of the specimen after tension test, we can see in the alloy with 2 parts of tin a lot of martensitic phase, up to 80% transformation, due to which this alloy shows these very, very good properties. Another example is development of microband-induced plasticity effect in the alloy with comprising titanium, zirconium, niobium, aluminum, and vanadium. This alloy was inspired by the alloy suggested by Zinkov and authors. This alloy comprises mainly refractory element of niobium and titanium zirconium. Shows it's a single phase alloy, but they demonstrate very interesting mechanical properties. This alloy shows very high strength, very good ductility at room temperature, and I guess most interesting, it shows very low work hardening. We modified it. We slightly modified the alloy proposed by Professor Zinkov and co-authors to make it cheaper and decrease its weight. The alloy was produced by vacuum arc melting. Then the obtained specimens was cold rolled to 80% and annealed in the interval 600, 1100 degrees C for 1 hour in vacuum to recrystallized microstructure. Structure characterization was performed using TEM, SEM including rigidity analysis, and phase composition was controlled by X-ray diffraction. Mechanical properties of this alloy was evaluated using tensile tests and Vickers microhardness test. In the as-cast condition, the alloy consisted of aqueous grains with the average diameter approximately 18 micrometers. The alloy was in this single phase BCC condition. After cold rolling to 80%, the alloy still was in a single phase condition, BCC lattice, and we also can observe quite typical microstructure with very high, typical for form condition, with very high dislocation density. Then this deformed alloy was annealed, and here you can see two examples of the alloy annealed at 800 degrees C and 1100 degrees C. At both temperatures, the alloy was recrystallized. However, if after annealing at 1100 degrees C, the alloy was still in the single phase condition, after annealing at 800 degrees C, the second Lavie phase was formed in the alloy. TEM analysis also shows the formation of very small Lavie space in the alloy after annealing at 800 degrees C. However, the fraction of the Lavie space was approximately 1%, which suppose does not affect noticeably on the mechanical properties of this alloy. After annealing at 1100 degrees C, we do not observe any second phase in the microstructure. The microstructure is single phase, but if you look at the diffraction spots, you can see the presence of reflection of the superlattice reflection, which suggests at least partial ordering of the microstructure. And we do not observe these superlattice reflexes after annealing at 800 degrees C. And if we look at mechanical behavior of this alloy, you can see quite typical behavior of cold rolled alloy with very fast flow localization and then netting and further fracture. But after recrystallization, the alloy shows more or less maybe similar behavior, which characterized by rather high yield strength, quite good ductility, and very low warp hardening, particularly in the case of annealing at 1100 degrees C. And this behavior actually very similar to the behavior of so-called gum metals, can be associated with low localization within so-called dislocation channels. If we look at microstructure of this alloy after small deformation, 7% of the recrystallized at 1100 degrees C condition, we can see formation of these dislocation channels in the microstructure, shown by arrows. And if we look at the right figure, if we look these dislocation channels, we can see that the crystalline lattice does not ordering in these channels anymore, while between those channels we still can see quite weak, but we still can see superlattice reflection, which suggests that between those channels the lattice is still partially ordering. And it looks like this very low work hardening is associated with the flow localization in these channels, and this the kind of microbite induced plasticity effect. In contrast, at 800 degrees C, we do not observe similar flow localization. Dislocation distributed quite homogeneously, almost do not forming these dislocation channels, which can be associated with the absence of ordering, partial ordering of the lattice. And finally, we have plotted at the BOM map a number of titanium alloys and titanium-rich high entropy alloys with different deformation mechanism, except of dislocation moment, of course. And we can see that this approach can be used in searching at least titanium-rich high entropy alloys with trip effect. Those alloys are located in the area with high values of both BO and MD. Less obvious whether we can use this approach for development of titanium-rich high entropy alloys which demonstrate microshare induced plasticity, because, for example, this alloy shown by green star is noticeably lower than the stability line, and another high entropy alloy demonstrating microshare plasticity well above this line. However, if we move to titanium-based alloys instead of titanium-rich entropy alloys, the value of this electron alloy design approach increases. Here you can see in the lower left part that titanium alloy demonstrated microshare-based induced plasticity, and gum metals were also located very close to the line of low stability of the beta phase at room temperature. And all these findings suggest that this approach can in general be used to predict effects of plastic flow localization caused by low stability of the discrete lattice. This is my conclusion. Thank you for your attention.
Thank you for your report. Colleagues, we have 2 minutes for question. If you have some questions, you're welcome.
May I ask one question? If the structure depends on the numbers of the paths, for example, you said that the summary reduction was about 80%, but it's possible to do for several variants. For example, for one pass, or maybe for several passes. And if there is a difference, is influence between numbers of passes and the structure, maybe quality, mechanical qualities.
Thank you for the very interesting question. I got it. Actually, we have not studied it in details, but recently we have performed several experiments. I'd say not on these alloys. We have done the experiments on the equiatomic hafnium, niobium, titanium, zirconium alloy, this one. And here the dependence. We have not yet studied the microstructure in details, but the response to the mechanical properties on the rolling conditions was quite weak. I'd say that's actually no difference in properties.
And one more question, if possible. If you try to use asymmetrical rolling, what about your opinion? Is it will be difference or not in mechanical properties? For example, we know that if you use asymmetrical rolling, you can change mechanical properties.
Yeah.
No, it depends, of course, of what kind of the symmetric you use.
Yeah, sure. I got a question. I think we should try. Actually, I don't know for sure yet.
I could say I can tell you that we have really unique asymmetrical rolling mill now in NMSTU, and we can collaborate if you want.
Probably, yeah, we can discuss it. Maybe.
Yes, thank you.
So thank you for your report. Please stop your demonstration. Okay. Next report goes from Karlsruhe Institute of Technology, Germany. Roman Kulagin, you're welcome.
Thank you very much, dear colleagues. Good day. Many thanks to organizer for this opportunity to give this talk today. Personally, I didn't know Alexey Zhilyaev, but my co-author Jan Bagelzimmer and Yuri Esterin, of course, knew him very well, and I know his works and his contribution to our field of research. So we also express our sympathy. Today, I will talk about high pressure torsion from mixing of solid components. Let's start. I have very simple outline of my talk. I will start with definition to clearly say what we are dealing with. Then I will explain which criteria for characterize mixing efficacy we developed. Then I will show our experimental results and simulations, and then I will show some outlooks. And I think in this part, it's to our opinion, it's very interesting that despite a lot of works in this field of severe plastic deformation, we can still find some fundamental challenges, some fundamental question, and it's interesting to develop this field also. So just to warming up you, I will start with two very common examples. First of all is coronavirus. Yeah, now a lot of countries of the world are dealing with fighting against this spread, this infection, and all of us very well know that huge amount of works were done in the field of fluids or powder mixing, or even for arts. So this painting actually was drawn by Mark Stock, and actually it's painting, you can buy it, but it was done by physical simulation. He used a flow dynamic approach to simulate how these colors can mix, and with his works, he also motivate people to study mixing. So just, I think it should be also interesting and can motivate us. So, as I say, I will start with definition. What we actually want. If we speak about mixing, if we use literature for liquids, then we should clearly understand difference between these two physical processes, stirring and mixing. Mixing means that we create new materials at atomistic level, so we mix exactly two components, and stirring is only mixing at mechanical level. So it's completely two different physical processes. And what we are talking in right now, it's only stirring. So in my talk, I will not consider some creation new alloys, new properties. I will talk only about mechanical mixing, or with other words, stirring. So we consider a high pressure torsion technique as a simple mixer. We don't care what we have, I mean, new alloys, new properties. We want to mix two components at some level and obtain very well mixed materials. Normally, if we start with stacked multi-layers, we have average size of these pieces nearly 1 millimeter. And what we want to have, we want to obtain very homogeneous distribution of these components at scale 1 micrometer. So to characterize this mixing, of course, if we have two components, we should definitely say about some scale, something, because if we have two components, it means that in our workpiece, we already have concentration of these components as we do it before our process. So if we want to mix two components at some square region, for example, with size L, and then to characterize mixing, we should analyze we should divide this region in small pieces with size L, this little one, and in this area we can calculate concentration, and we proposed for the first time ever, we proposed an index of mixing efficacy. It's based on Gibbs parameter. So Gibbs parameter is this one, and if we analyze it, it's very clear to understand that as small as this parameter is, it means that the beta mixing we already have. And just to normalize these Gibbs parameters in order to have 1 for completely inhomogeneous distribution and 0 for very nice homogeneous distribution of components, we propose this index. So here you can see our equipment for high pressure torsion. It was produced by Clement. And in my talk, I will share results of experiment of two systems, aluminium nickel and cuprum molybdenum cuprum. So in first case, we took multi-layers of 25 foils with this thickness, and it was standard constraint anvils and more or less common parameter for high pressure torsion experiment. So for this system, we did 5 turns, and for cuprum molybdenum cuprum system, we take only 3 layers and bigger than in first case, and for this system we did 4 turns. So here you can see a result of our experiments. We did 3 cuts of our sample after high pressure torsion and took some parts of this microstructure. And if you look at this slide, if you see, you can say that, of course, this mixing is improved from left to the right. And but actually, in a lot of publication, we saw similar picture, but how we can, now we propose to analyze this quantitatively. So how this mixing is improved. Yes, and for this purpose, we analyzed the change of our index with increasing of strains. And here we can already speak about 2 interesting results. First results is that the mixing, the steering of materials under high pressure torsion has, exactly for this case, we saw 2 different levels. So first one, when the layers start to fold or somehow destroyed, but still the mix is not happens actually. And after we reach some levels, for this case it was shear strain 120, the mixing efficient goes more faster. And according to this trend, if we increase the deformation, then we should reach completely intermixed layers. Next, our experiment was with system kupfer molybdenum kupfer. After high pressure torsion, we cut a lamella from our sample, and then we use computed tomography. We did about 1000 cross section, and then connected in one animation. So in the next slide, I will show this animation, how the change of structure during the experiment. And to have some idea about the strain level, we can say that in the middle we have shear deformation nearly 0, and at the periphery, at the edge, we have nearly 250. So now this animation. Maybe it not so surprising if we see some vortex in liquids or gas. It's very famous instability, like Kelvin-Gelgoltz instability, and we can observe this if we see some clouds with this vortex shape. But in solid state, it's actually new and interesting, because with this velocity which we used for deforming our materials, actually this instability cannot take place. And second thing, that if we see this picture, it looks like something happened, this layer start to rotate. But what we can say about mixing, is it really intermixed or still not? And we also used our index to characterize mixing during this process. And as you can see here, actually this distortion of layers, instability, didn't lead to mixing of these components. Actually, it stayed nearly 1. That means that these materials are not mixed well. So today we also saw a few talks where people say what they did to make this mixing more efficient. And what we proposed is actually make this high pressure torsion anvils with some inclination. If we put our sample with some angle, then we will mechanically create some additional folding of some intermediate layer. And due to this folding, we can mechanically improve this mixing. So we didn't try this experimentally, but for example, from work from Professor Langdon, he also observed if they produce anvils with some irregularity, for example, if anvils has problem with axis, then he also observed some mixing, some vortex in high pressure torsion sample. Okay, and now I want to speak about, talk about some fundamental questions that arise in this field. First of all, we should speak about instability criterion. So already we have a few theory, some assumption why this instability happens. From our point of view, the reason for this instability is some obstacles that block this simple shear and lead to some rotation. But other people also develop other theory, other ideas why this instability can happen. But right now, nobody can definitely say, okay, if you take aluminum and iron or some two pair of materials, that exactly when you reach the shear strain 100 or 200, these instabilities will start. So first task is to develop this instability criterion. Second very interesting question is fracture of solid body inside other solid body. It's also very interesting, but during high pressure torsion, we have high pressure. And if fracture of some levels inside materials happens, then the soft materials can fill gap between hard materials. And actually our samples will always looks like solid bodied, but actually some fracture happens inside. It's also interesting to analyze this mechanism. Next one is minimum fragment size. It's very famous works from liquid. So if we have some turbulence flow, then we can predict which smallest drops in this liquid flow can happen. And more or less, it would be also interesting for metals. And last one, as you see, during this instability, different patterns happens. It can be faults like in the slides with aluminum, nickel, or it can be some vortex like for kupfer, molybdenum, kupfer. But we also observe some very interesting patterns. And the question is, if we know that shape of our composites played important role for the composites properties, which properties we will have if we create materials with some vortex patterns. And I want also to share our last work. So the idea to combine soft and hard materials in order to create some advanced properties is actually not new. Some idea, today we heard the talk from Hyoung Seop Kim or also Yulia Astanin. They already published a few papers where they say that if we combine hard and soft components in special design, special form, we can enormous, so we can create materials with fracture resistance, for example, or other interesting properties. So what we proposed, what we found that actually this pattern that we observed, and here it's not only high pressure torsion. Here you can see some structure after IRB, YCAP, and twist extrusion, high pressure torsion. So actually, if we work with composite materials and with severe plastic deformation processes, we can create very interesting patterns that we can also see in some rocks or lithosphere. And our idea to mimetic this process, like biomimetic, we inspired from bio structures, and in lithomimetic we look not in the structure but in these processes. Actually, all processes in our Earth happens with shear and with big high pressure. So it's simple shear deformation and high pressure. Okay, and I came to conclusion of my talk. So I think this message you can take home. So first of all, high pressure torsion acts as mixer and enabling steering of metals in solid state. And second one is we propose a new index of mixing based on Gibbs parameter, and it can be used to characterize these samples. Thank you for your attention.
Thank you for such interesting report, because I think this is the most beautiful microstructures today.
Can I say, it's just a comment, a kind of compliment. You presented your work with flying colors, figuratively and literally. There is such idiom, like to do something with flying colors, and it was, you're doing something interesting, really interesting. I'm sorry.
Thank you very much.
I'm sorry to interrupt.
Okay. Colleagues, we have 1-2 minutes for...
Dmitry, may I ask the question, please?
Yes.
Maybe not a question, but maybe a piece of advice for the researcher. In the area of metal deformation, of metal processing, there exists the theory of joint plastic deformation of different metals. This theory was created by Grigory Arkulis in 60s years of the last century. He was the scientist of our university, north of Magnitogorsk State Technical University. This theory was well known and is well known in the area of metal deformation, when two metals with different mechanical properties are deformed jointly. He created his theory based on the research of such methods of metal processing as drawing, rolling, and others. His book was published in the USSR, and it was translated in the USA, and also it was published in English. In my opinion, that area of your investigation is close to his researches and the results which were obtained in Russia in that, and maybe it will be reasonable for you to study that researches and to use them for your area of investigation. Thank you.
Thank you very much. So, colleagues, we should go to the next report from Vadim Sheremetyev. Vadim, are you here? I don't see him. So, what should we do in this case? Should we wait, Professor Peshin?
It will be better to wait for 20 minutes, because if somebody wants to listen, anybody else, it's only one thing to wait for.
Okay.
20 minutes.
So the next reporter is Andrey Volokitin from Rudny Industrial Institute, Kazakhstan. Andrey, are you here?
Almost. He's now at a business trip, and he asked me to make the report instead of him.
Okay, no problem.
Okay. Hello, everyone. My name is Evgeny, and I will make the report at the next SEM. Thermomechanical treatment of steel using severe plastic deformation and cryogenic cooling. The plan of the report is first introduction, purpose of the work, materials and methods, results and discussion, and in the end, conclusion. Today, the great attention have the studies of methods that allow to obtain an ultrafine granite structure. The most well-known method is severe plastic deformation method. And here you can see the most well-known SPD methods. It's equal channel angular pressing, sweet extrusion, and high pressure torsion. High pressure torsion is one of the most well-known methods of severe plastic deformation for obtaining of UFG structure. The geometric shape of the sample in this method can be disc form or ring form. And relevance of this study is the improving the performance properties of piston rings used in internal combustion engines by thermomechanical treatment using SPD and cryogenic cooling. The purpose of this work is investigation of HPT process in the die of new design of stainless steel AC 300-04 using cryogenic cooling. Here you can see the possible variant of stamp for HPT process. In this stamp, the main principle is the double helix system. Periodic spiral groove of the same shape and size are created on two contacted surfaces, on the punch and on the deforming element. When punch movement towards the deformed elements will be rotate. The initial workpiece in the ring form is laid in the cup, and it obtain two movement pressure from punch and rotation from deformed element. At the first stage of investigation today, it was conducted a computer simulation in the deform package at the next condition. Initial workpiece had an annular shape with a diameter 76 millimeters, width of 3.5 millimeters, and thickness of 3 millimeters. Deformation was carried out at two temperatures, at amber temperature 20 degrees and at the Kulagin condition minus 196 degrees. The speed of the punch was 1.5 millimeter per second. Friction coefficient between billet and deformed element was 0.45, and the friction coefficient between punch and the deformed element was lower, 0.1. As the form doesn't have the material data at Kulagin condition, we will create new material file with the material data taken from this reference. At the first stage of computer simulation, it was studied the strain state. As during deformation, the size of cross-section of workpiece doesn't change, it was possible to estimate the percent fraction of different strain zones. First pass, second pass means that deforming tool made full rotate around its axis. In other words, 360 degrees. In this scheme, it will make after 3/4 cycles, because each segment has an angle of 90 degrees. After first pass, the most zone in the cross section has a very low strain value. It can be considered as unprocessed zone, but the most high strain values obtained in the inner face of the ring, about 3.5. After second pass, the distribution of strain moved towards from inner face of the ring to the center. After third and fourth pass, we obtained that unprocessed zone almost gone, and the most processed zone has the strain more than 5 in the inner face of the ring. Comparative analysis of both models at two temperature showed that the strain state in both cases is almost identical, but during consideration stress state, difference was more different. With cryogenic cooling, the level of compressive stresses is more high, about by 20%. Here, the average stress in the cross section is 3,200, and here the average value of stress is 3,800. But due to the too small cross-section area, it's about 10 square millimeters, it was decided to use complex indicator of the stress strain state, the Lauderdale coefficient. It is calculated by this equation. where components of formula are main stresses. And the value of the coefficient varied from -1 to +1. And the value from 0 to +1 corresponds to compression, from 0 to -1 corresponds to stretching, and the value of coefficient tending to 0 corresponds to shear. Here you can see the scheme of indication of measurements on the all 4 faces of the cross-section area. And after calculation of Lodin coefficient, it was revealed that on the all 4 faces of workpiece, the main prevalation of the shear deformation. But if we will consider in the diagonal direction, so this corner and this has a similar condition. This corner we can consider like a dead zone without any rotation, and this corner will be the most processed because here this zone of metal obtained rotation from this face of the deforming die and this face. So here we have on the half of the length of this face the shear deformation and some fraction of compression. On the next 3 faces we have similar condition. And after strain state investigation, it was decided to make the microstructure evolution simulation using the cellular automata methods. In the last deform version, it was very improved the mechanism of simulation by this method. In particularly, here you can see the recommended values for different material like aluminum, nickel, and steel for better simulation results. The initial grain size was assumed to be 12 microns. And here you can see the results after 4 pass in the most processed zone in the inner face of the ring. At the ambient temperature, it was average grain size about 0.8 microns, and at cryogenic condition, it was a little bit less, about 0.6 microns. And the conclusion, we can talk that this implementation of high pressure torsion in the stamp of new design, the main idea of development of such instrument is possibility of HPT realization using simple common forging equipment. For example, like simple hydraulic press. Because of in this case, we don't need to build or buy special unique equipment for HPT processes. And at the next stage of this investigation, I think till the end of this year, it will be performed already first stages of experiments and already investigation of microstructure and mechanical properties using aluminium and copper. And a few words about Professor Zhilyaev. Unfortunately, I didn't know him very well as most of you. I had met him 3 years ago at the Magnitogorsk rolling practice workshop. And based of words that I heard today, I understand that he was not only great scientist, but also very friendly and open-minded person. Well, thank you for attention.
Thank you for your report. So, colleagues, we have about 3 minutes for asking questions. Okay, one moment about your simulation. Did you use microstructure simulation by Deform 3D?
Yeah.
Directly? Yes. How to but why did you use cellular automata multi-scale simulation? In general, this is multi-scale simulation, but usually people create some kind of representative volume elements and make different calculations directly in Abacus, for example.
Well, unfortunately, we didn't have an Abacus license in the first. And you're right, in the deformed system, there are 2 ways to microstructure simulation. Cellular automata, and second is common distribution of parameters like strain, stress, and many others. And more, if with let's just call this matter gradient parameter because of we have a gradient line of different colors. In this case, we can estimate microstructure in wall volume of workpiece, for example, in wall cross section. But in this case, we have a disadvantage. We can estimate only size, digital size of grains. And cellular automata also have advantage and disadvantage. The main advantage that in this case we can possible to estimate both size and possible shape, but we can make it only on the certain points of the workpiece.
Okay.
So we decided that it will be more visible results.
Okay, thank you. So, and thank you. Next,
Thank you.
Next speaker is Yulia Kuzminova. Kuzminova, yes.
Yes. Do you hear me?
Yes, from Siberian Federal University.
No,
Russia.
no.
No. Skolkovo Institute of Science and Technology, Russia. You're welcome.
Do you see the presentation? Good. Good evening, good day, good morning. maybe for someone. My name is Yulia Kuzminova. I'm a PhD student in Skolkovo Institute of Science and Technology, and it's a pleasure for me to present my current work, performing the high entropy alloys by additive manufacturing. And actually, it is it work continuous the study which was done with Professor Zhilyaev. And just to remind you, the definition of high entropy alloys, it's the alloys which contains at least 5 principal elements with in approximately equiatomic ratio. And by this slide, you can see how the manipulating the the value of one element in the composition can change this the structure, the crystal structure of the material, or mechanical properties of this material. But searching of the particular composition of this alloy with the required properties, or performing the solid parts with these alloys can be challenging. So we decided to try the approach to produce the high entropy alloys with additive manufacturing techniques. And for this task, we used the powdered bed fusion techniques, also known as selective laser melting. As you well know, its techniques allows to build the solid parts layer by layer by adding the metal powder from the feeder and using the roller or blader and melt the powder according to computer geometry with different heat source. It can be laser or electron beam. So in our study, we started with 2 metals, the 4 components metals, which is well known, investigated, and we add the pure metal powder to this. As you can see, the quality of the alumina powder is not really satisfied, but due to the fact that it's not the high value of the alumina in the powder mixture, we decided that the spreading of these powders will provide the good quality. And the next step is choosing the printing parameters for perform the samples. We was limited in the materials, so we decided to choose printing parameters based on our results for stainless steel. The stainless steel and 4-component high entropy alloys demonstrate the similar printing behavior. So we chose the printing parameters which provided the deepest penetration of laser to the material. And we assume that such remelting process through the several layers will provide the homogeneous element distribution in the materials. So as a result, we print 3 platforms with different ratio of 4 components alloys and alumina powder, 0.3, 1.2, and 3.0, and investigated 12 regimes. As a result, you can see the micro hardness of porosity which we estimated. Interesting that we only by adding 3% of alumina powder, we see the difference in the micro hardness, and this difference is not very great, just about by 20-30 HV. But interesting result we obtained for porosity. These dots, 3 gray dots, present the alloy without alumina, and all samples for each, depending of the, no matter which printing process parameter we choose, demonstrate the lower porosity compared with the pure four-component systems. We suggest it's because of the low melting point of alumina, and possibly it's the alumina during the printing. Alumina close the pores, which can be estimated by optical methods. Of course, we add the some volume of alumina, but how much aluminum we have in the material in the end. So we found that about twice lower value of alumina we can detect in the material. As you can see by this analysis, the alumina for all three regimes, all three conditions are quite, the alumina have the homogeneous distribution, but actually we don't really believe in this result. And then on next slide, I will explain you why. So here you see the structural analysis. By this backscattering images, you see that the difference of the in the structure we see on the last for the last condition, for the third platform where was the we add the 3% of alumina, and the other demonstrate the cellular structure. The similar as for the four-component systems. And here we see the zones, even zones with looks like spinodile decay, and the quite the same structural features was presented in other research. And this is the slide which demonstrates why we're not sure in the EDX results. As you can see, according to XRD analysis, the four-component systems, it is a pure FCC structure, but with adding alumina, we also see the FCC structure without new peak, but we expected, as you remember on the first slide, that the adding of alumina transforms the structure from FCC to BCC. So, and here we see nothing. So maybe it is because of the high coolant rate during the process. So maybe the annealing of the material will transform the structure from the FCC to BCC. But according to this analysis, we see that the FCC structure is stable. So discuss the EDX result. We suggest that this is the small area which we found. It's just one area which contain the homogeneous alumina distribution, but on the if we analyze the bigger area, there will be the segregation of alumina. We analyzed with EDX the big area, but we didn't apply mapping. And we found that the value of alumina is twice lower, as was demonstrated in the table. But maybe the segregation of alumina in the powder it's really high, and generally it is FCC structure with which is not rich of aluminum. And in this slide, you see the density and lattice parameter estimations, and quite predictable results. The density decrease with adding of alumina, And here you see how much alumina we add in the powder mixture. It's not how much alumina in the material. And you also see that the lattice parameter decrease with alumina, with adding of alumina. And the main conclusion which we can make that it's PBF techniques, with PBF techniques, it is possible to produce high entropy alloys, but anyway, there are questions about the homogeneity of this of the elements in the printed alloy. So in the other statement, just repeat that those which I said during the presentation. So thank you for your attention, and I'm happy to answer your questions.
Thank you for your presentation, colleagues. Do you have any questions?
Dmitry, may I ask a question, please? Did you use any protective atmosphere during additive manufacturing process?
Yes, of course, it was in argon.
So you didn't notice any oxidation of powders or especially of aluminium during this process?
No, we know that the level of oxygen in the chamber also control. It is less than 0.3%, but for example, when it is not enough for titanium. So possibly then we print the mixture, there are increased, it's possible that there will be the oxidation of the material. It's possible.
Yes, because it will influence the mechanical properties and other properties of the material in general. And as a result, it may lead to the broke of the part of the manufacturer.
We will monitor it. Thank you.
So, more questions? Professor Pesin.
Okay. Julia, you have a mixture of the powders.
Yep.
At the beginning, but what do you think if there is influence between the geometry of the geometry of the powder and about and the size of it? Because you can change not only the volume of the elements, but you can change maybe geometry of the power of the one piece of power.
So you suggest maybe we need to use the powder with lower mean size distribution.
With size, you can change size, of course, and you can change geometry. For example, it could be circle. It could be maybe
the shape of the morphology of particles, yes, of different particles, because they may be like a pin, like a sphere, and so on and so forth.
Because you change the border line between the elements, and maybe this the length of this border you can change, and maybe it's influence for something. I don't know what is.
Yeah, yes, it is possible. Actually, I found several articles which mixed. So in our case, we mixed powder very gentle, not to smash it, the not strong alumina powder. But other research, they make the very harsh regime of in the milling, in the wheeling, for the wheeling, and they just mixed the powders of one material to another. It's like, it's looked like penetration. It was Roman presented our
yes,
with these beautiful pictures also. So yes, actually it's kind of influence, and we need to search the ways to obtain the better result.
I think that maybe it's interesting to have to take some ideas from Roman presentation.
We'll work on it.
In your research too, of course. Thank you for interesting presentation.
So thank you, colleagues. I'm trying to find the last two speakers, Sergey Zherebtsov and Valery Danilenko. Are you here? Valery Danilenko, Institute of Metals Plasticity Problems, Russia. So you're welcome. Thank you for your attention.
Good day, dear colleague. Can you see my presentation?
Yes, everything is okay.
Good. The first, thank you for the possibility to speak at conference in memory of Alexander Petrovich Zhilyaev. The report is good. Kappa aluminum metal matrix composite fabricated by accumulative high pressure torsion. My name is Valery. My colleagues Alexey Korchunov and Dmitry Gunderov. It is content my presentation. High pressure torsion and its evolution, accumulative high pressure torsion. 3-layer stack, kappa, alumina kappa, metal matrix composite obtained accumulative high pressure torsion and other investigation method. Bulk nanostructure materials are obtained using several plastic deformation method. High pressure torsion is one of the unique several plastic deformation method. A significant contribution to the development of this method was made by Alexander Petrovich Zhilyaev. Just look at the list of his publication dedicated to high pressure torsion presented in this slide. This is the first review on the high pressure torsion method. 2 monography or 2 book on this topic, including the one that come out this year. In this book, the 3rd chapter is about high pressure torsion. Evolution high pressure torsion may be called accumulative high pressure torsion. Dmitry Gunderov and your colleagues proposed to develop the high pressure torsion method as a cumulative high pressure torsion. The essence of this method is that the deformed sample by the high pressure torsion proceeding and cut into 4 parts. This part stuck in on anvil and deformed under the same condition. Cut and deformation, such cycle can be carried out several times. My goal of this report is a comparison of structure kappa aluminum metal matrix composites fabricated by traditional high pressure torsion and accumulative high pressure torsion. In this slide, you see traditional obtained kappa aluminum metal matrix composites proceeds by high pressure, traditional high pressure torsion. In this slide, cuprum alumina metal matrix composites processed by a cumulative high pressure torsion. 3 lower kappa, alumina kappa, stuck on anvil and deformation, cut into 4 parts, stuck and stuck it on anvil and deformation under the same condition, and obtain this subject, this object, this disc, this metal matrix composite. It is samples for investigation made traditional HPT, 3 lower kappa, aluminum kappa, pressure 6 GPa, room temperature, rotation speed of 1 rotation per minute, and 10 turns processing. Accumulative high pressure torsion, it is similar, but step 1, 3 lower disc kappa, alumina kappa, deformation in this condition, and 2 turn. Step 2, cutting on 4 parts. The parts were stacked on top of the high pressure torsion anvils on top of each other, and revolution 2 turns. Repeat cutting 3 times. The step 3. After third cutting, the stack was deformed by 4 turns. Scanning electron. The cross-section structure was investigation in detail of the zone of the center, and the Edge obtained sample. This is sample after a traditional high pressure torsion. It is same picture. The bright region denote kappa rich phase, this and this, and the dark region denote the aluminum rich phase, and left, and it is composition map for kappa element, and this green and red, it is element of alumina. You see very small mixed this disc. After accumulative high pressure torsion, the accumulative high pressure torsion gives strong mixed in the center. Composition maps confirm this. It is scanning electron microscope. It is composition map or element map, kappa alumina. The Edge after high pressure torsion. You see a weakly mixed structure NZG on on sample obtained traditional high pressure torsion. This KEDG after accumulative high pressure torsion, you see mixed ZG on the sample, which is slightly weak than the center of this sample, but much more than the sample after the traditional high pressure torsion. X-ray diffraction analysis showed that the sample after traditional high pressure torsion contain only the red line contain only diffraction peak of copper and alumina. The patterns of sample fabricated by accumulative high pressure torsion, the blue line, confirm the present at aluminum, copper, and intermetallic compound, copper alumina 2 and copper 9 alumina 4. In this slide, you see fragment X-ray diffraction pattern from obtaining copper aluminum composite. You see intermetallic compound after accumulative high pressure torsion. This is my summary. Analysis by high ray diffraction, scanning electron microscope, and element NTDX method showed the formation of intermetallic phases in the lower structure during accumulative high pressure torsion. Thank you for attention.
Thank you for your report. Colleagues, do you have any questions? Okay, I have one question just for discussion. What do you think about industrial application of such method, high pressure torsion? Is it possible in perspective?
I think in present time we have only fundamental physical application, but solid state reaction and solid state reaction in metal.
So, colleagues, do you have any questions? Okay. Thank you for your report. The first day is over. Everybody who was online during the whole day, thank you for your attention. Please check our website for actual program and actual links to Zoom conference. We will try to save the same links and data of conference for Zoom Tomorrow we will start on 8 a.m. in Moscow time from plenary session of Professor Megumi Kawasaki. It will be interesting. I think see you soon. Bye-bye.